me? Can you all see me? Can you see me, hear me? Yes, I hope. See me, hear me? Everyone can see me, hear me, I hope. I have been chasing a mosquito in this room. So it's biting me like crazy. So if you hear me go, ow, we have a random mosquito in this room and I can't get it. So for today, it's the mosquito's fault for me being late because I really didn't want to be distracted, but I think I'm going to be distracted today. So sorry about that. Anyway, hello everyone. Thank you for waiting. I apologize for the delay. I'm like already a little glowy. And I'm petrified of what's going on down here. So if you see me kind of, looking down, you'll know why. I keep getting bitten. So hello, thank you, Jerry, and I'm sure Mike, Jerry Ryan and Mike Richardson. They are the moderators of this mini course. And you know what? I will get to that in just a second. Let me put up. Whoops, where are you? Hold on. There you are. Okay. So let me put up the title of this course. Oh, and I need to flip this. Hold on, guys. Yes, me chasing the mosquito so much has prevented me from ensuring that I actually have a working view of you all. Okay. This is now the second chef. We are at the very end, essentially. We're doing our ground effects courses. This is the series in which we take everything that we've learned from both the first and the second chef, and which means basically from sun all the way, believe it or not, finally to mud, right? That's actually what we call it in aerospace. And yes, this is, if you are a new person just joining us, I will do my best to try to get this to be a bit, understandable for you, but it does build on other courses. So, and I will go over a little bit about how to find those courses in a second, because I've actually had quite a few people ask me about this. I have yet to put up any type of like tutorial that tells you which courses to go through when. So I will go through a little bit of that here in a second. But the first thing I wanted to say is hello to everyone. I see lots of people, including lots of VIPs joining us. Thank you so much. Both Jerry Ryan and Mike Richardson are VIPs. They also are moderators here, so be nice to them. Hi, Jerry, I see you. I do have my phone on me, so if my mic goes out, which it might, I'm not sure what the quality of these batteries, and I have several others on the ready here. So just ping me if my mic goes out, and I will quickly switch. Okay, let's see what else, what other little technical things. Yeah, if you have questions in the chat and I don't get to them because maybe they scroll by too quickly or something like that, ping Jerry and Mike or put my name at me. That will highlight my name, and I'll have a tendency my eyes will tendency to go to those. But yes, if you continue getting frustrated that I'm not responding to you, it's not because I'm ignoring you. Oh, I keep getting bitten. It's not that I'm ignoring you. It's that things have just scrolled by so quickly. So ping Jerry or Mike and say, hey, can you really get this to Tamitha? And I always look, when I see their blue names, I always look to see what they're saying. So that is one way to get hold of me. And then outside of that, I will be, for all the Patreon folks, I will check both, not just this chat here at YouTube, but I also check the Patreon feed. So if you have questions there as well. I do have a couple extra slides that I've added to this course because of Patreon members who have been pinging me about questions. So I will address those as best I can. Now, speaking of Patreon members, thank you so much. This is my VIP steering committee. All these folks help steer the ship. They kind of they help us decide where Space Weather Woman's going to go next, what she's going to do, what things are the most important to focus on, what data products I should be developing or including in space weather forecasts, and really who are the stakeholders and how they should be prioritized, because there's a lot of people that try to get the attention of this community, and really these are the folks that help me decide what are the most interesting things to tackle. Okay, is this a problem? Who is calling? Check, check. No. Nope, it's a telemarketer, of course. Sorry about that. But these folks are the ones that help steer the ship. They're the ones that basically help me prioritize what challenges we might be having, and really what are the most important aspects of space weather that need to be either communicated or elucidated for everyone else. So my hats off to them. I thank them very much, especially some of these people on the top here who are really donating an immense amount of money, and I'm just very, very grateful for all of you. And then, of course, everyone else is my friends and family. Oh my goodness, I would be lost without them. And then everybody on this side, these are the people who actually help decide what are the mini courses, what we're going to be doing, what we're going to be teaching, what questions I should be tackling, what slides I should put up. And these folks are just I just love them dearly. Many of them have been with me for a very long time, more than a year. And can you believe it? We're finally getting through the entire space weather basics, which is the first chef from sun to the near Earth space, and then the second chef from near Earth space all the way to the ground. So I feel very grateful that all these people have been with me pretty much through the whole thing. So please join us on Patreon. You'll get lots of stuff, not just mini courses, but lots of other opportunities there to interact with me. And before I get started on the mini course, let me just go ahead for those who have asked recently, how do you find the space weather basics, and what are they good for? I mean, which ones do I start off with? Because I've been doing mini courses now for about 2 years, maybe longer than that, maybe since late 2018. My goodness, it's been a while. Woof. Wow, longer than that. Okay, so I've been doing mini courses for quite some time, and so we've got quite a few of them now, and they're all set up in different series, because each subject that I tackle ends up taking longer than just it's more than just one take. So I'm getting bit. The mosquito is right here. Oh my goodness, I wonder if I can get it. He is right here. He's already bitten me like 3 times in just like the last 2 minutes. Ah, my goodness, my legs are driving me crazy. Okay, sorry. This is a very strange mini course. Okay, so the first, what I'll talk about is that if you go to the C course series, this is the course series on coronal mass ejections, and this is really where the course series starts. Okay, and they're basically kind of in order. So you'll see the C course series, the F course series, P courses. There's all sorts of them. And I think if I go here and you click on them, yeah, let's not play that. How do I get to? Well, shoot. Okay, here we go. Hopefully I can get to the actual description. Yes. So if you go to the C course series, for example, you will see up in the top, whoops, standing on the wrong side, up on the top portion, here's the title. Here are the number of courses in the series, right? We've got 3 videos here, and you can see them on this side where you can click in them. But then you also have down here is the description, and this is super important. And the reason why is because this talks about not only what is in the courses, but it also down here talks about the prerequisites. Okay, so as you can see, the prerequisites for the C course series are none. Okay, so coronal mass ejections is really where you start if you want to start learning about the basics of space weather. And really, we start with coronal mass ejections simply because that's actually how the field started, right? We started realizing space weather occurred, yes, because of solar flares, but we saw these big things coming out of the sun and in the sun's corona, and we wondered what they were. So we started flying equipment and instruments, and we started flying instruments in space, and kind of like how I kind of build up on it. I build up your understanding of space weather very similarly to how we really did in the modern age. Once we became a spacefaring, in the sense that we have instruments and spacecraft that we can actually launch out there that will survive and take measurements. That's kind of how the field of space weather evolved. And so I take you on that journey, really very much like a scientist that of old who was discovering all these amazing things. And so I wanted you to see that that as let me see if I can now go back. I'm gonna have to take this off of maximum here. If I go back one more time. So once you go from the C course series that talks about, whoops, I've got something playing here still. Oh, for goodness sake. I'll kill this in a second, so let me mute this. So after you get the C course series, that's all the coronal mass ejections. Then the next one is the F course series. Okay, so this is F for flares. So C for coronal mass ejections, F for flares. And again, if you look at the playlist, you'll see the description. You'll see the number of courses here. In this case, there's 4 courses, okay, in the flare series. And then you'll actually see the description. And look, suddenly, prerequisites, course C1, C2, and C3. So you need the C course series to really understand, because we start building on that C course series. And we start learning how flares are related to coronal mass ejections and really how they're different, and why we made the mistakes we did as scientists early on. And it kind of, once again, it kind of gives you an evolution of the field along with understanding the phenomenology. So that is really how you go about looking at these courses. And if you're looking for where to start, obviously the C course series, this playing, obviously the C course series is the beginning, and then it goes all the way on clear into W's for wind. H goes into heliosphere, and then we go into M, which is the magnetosphere. This is where the second chef begins, because this is now near Earth space. And then we go into I. The I course series is next, and then the E course series. And the E course series is what we're doing now, because E is for Earth and E is for effects. So it's ground level effects at Earth, right? So that's why I call it the E course series. And that now gets me back to here. So now you understand why this is, when you look at it on YouTube and you see the title, it's called the E course series, okay? And wow, I hope that mosquito got his fill, because my legs are itching. What I sacrifice for you. I'm kidding. Okay, so what I'm going to do here, since this has a lot of the review charts, and it has a lot of the charts from the last time I taught this course. And I did that on purpose, because if I get questions, I want to make sure that you all see it. And I mean, I have access to be able to show all of you all of this stuff. I had COVID back in June. And so if you're wondering why it's been so long since I gave a course, because I gave a course in May, if you're wondering why it's been so long since I gave a course, it's because I had to recover, because these courses take a lot out of all of us, I think. And I just did not have the stamina. So what I'm going to do, because it's been so long, I'm going to review just a little bit and remind everybody. I know for those of you who have seen this so many times, I know I sound like a broken record, but it's so important that you remember that everything on the ground, everything in near Earth space, everything to do with the second chef has everything to do with the Earth's magnetic field. It orders everything, okay? So this is once again to remind you that yes, the Earth's magnetic field has a particular shape, right? The main component of the Earth's magnetic field is the dipole field, and this is not the greatest representation of a dipole field, but it sort of is, right? So what you're looking at is magnetic field that comes out in loops. The loops really don't touch. Each loop locks in, they're nested, so that the inner loop, it reaches Earth inside, the outer loops get further and further out, right? And what that means is that as you move up toward the poles, you are going higher and higher in latitude, obviously, right? So that means that each one of these has a unique place where the loop has actually got its, what we call the foot points at the Earth's surface, right? Because these don't all come together in a pinch and are in the same place. They actually have distinct latitudes. And we map those down here, okay? You can actually tell which loop kind of lands in what location. We call these L shells, right? L shell, and if you go back to the M course series, you will see the full definition of an L shell. It's defined essentially in the equator region, and it's basically the distance away from the center of Earth. So L of 1.5 is here. Why? Because that's L of 1, and then about another half Earth radii is out to here. So that's L of 1.5. Here's L of 2, L of 3, L of 4. Why do we not define them up here? Well, as you can see, even L of 5, right? It's only 5 Earth radii out at the equator, at the magnetic equator. It's not 5 Earth radii out way up here, but L of 5 is still here. It's a lot closer to Earth. As a matter of fact, here's now it's at what would be considered L of 1, right? It's only 1 Earth radius, but that's not where you would define L. You define L here. So if you were to map this out, you would be 5 Earth radii out, clear out at the equator region, and that's L of 5. Why that's important is that as you wiggle this field line, those wiggles make it all the way to here. They don't wiggle down here, they wiggle up at this latitude. And so we see when you wiggle the magnetic field at L of 5, you're wiggling stuff that's up at these high latitudes. See, so suddenly you start realizing, oh my goodness, we can kind of tell what's going on out in space and whereabouts it's happening just by looking at the ground and seeing which area, which latitude is magnetically disturbed. Because these wiggles translate all the way down. Neat, huh? Well, this is one of the things that they realized early on. Because when they would see disturbances from these big, coronal mass ejections that would come out, they would see that the Earth's magnetic system would get disturbed, and it would make patterns on the ground. And the more magnetometers they laid all around the place, the more patterns they would see. There was actually a method to the madness, and it was a matter of trying to figure out how do we suss this out. Well, as we started getting maps and understanding of the Earth's magnetic shield, we started making more and more sense of this, right? And now it's so well known, it's a tool. We have satellites in space, right, in nearer space in these different locations, and they are literally coordinating with people on the ground and the magnetometers on the ground. And you're seeing lots of studies, tons of studies. We've been doing that for decades now, where you see lots of ground-based observations being used in tandem with satellite-based observations. Right? Now, of course, I'm not going to go into the whole Earth system, what it's all about, and all that kind of thing. That's been done. We've done that ad infinitum. We've done it on. We've also come down into the ionosphere. We talked about current layers and all that kind of stuff. And I'll just remind you, in case you don't recall, how messy it is. Remember this. Hopefully everybody remembers this and goes, oh God, I hope I never had to see that again. So this is one of several diagrams that should give you slight headaches. This is one. There's another one I'm going to show you in just a minute that's talking about the current systems as we set this out. Mainly the reason I'm showing this is because this focuses on the ionosphere, and it shows not only do we have inbound and outbound currents in region 1 and region 2, we call these field-aligned currents. Remember, the magnetic field is penetrating in this region, okay, because this is the polar region. Here's the sun, in case you didn't remember. Sun is coming in this way. Here's the equator. You can see it, the dashed line here. Okay, this is probably the terminator relative from the perspective of the sun. So day side, night side, right? And so you have currents and convections that are driven in the day side ionosphere. You have convection and currents that are driven in the polar regions, both north and south. And then there are some other types of currents that are being driven on the night side. You also have, of course, downwelling gravity waves, all sorts of convection that's occurring from high latitude that couples into low latitude and vice versa. This is one of the reasons why the auroral electrojets are such a great indicator of, sorry, got bit again, are such a great indicator of aurora, even though the auroral electrojets actually are lower than the aurora typically is. You still get a lot of understanding from that. We talked a little bit about AE index, which I'll go into again, right? But before I do that, let me give you a slightly bigger impression, a review. Yeah, I think I'll do this one. Oh, my legs are just on fire. Whew. Okay. So I'm going to stand over the words here because we're not really using the charts the way that we had. I don't really know. Maybe I won't use that one. Hold on. I don't really want to talk about the belts. I'll use this one. Here's one. Yeah. This one focuses just on the current systems. So when we look at the larger scale of things, remember this is Earth here, right? The sun is out here, and you've got shooting solar wind in this way. Here's kind of the teardrop that is the Earth's magnetic system, right? You've got a solar slinky, not a solar, I'm sorry, Earth's magnetic system that's got this toroidal, remember me talking about this? The dipole field sits, I mean, the Earth's system fits here, And you've got the dipole field that goes in this way. And if I sit this slinky this way, like this, and you imagine Earth is inside it, right? Kind of sitting it like this. Okay, that's the heart of the Earth's magnetic system. So this is the dipole field that we were talking about. And it, of course, extends out further, right? So it extends out in front. And so you're seeing part of that magnetic field line. That's one of these slinky things coming up like this. Okay. So here, and then even further out, right in the front end of the Earth's magnetic system. So just to remind you of what the shield looks like, right? And in this case, the magnetic field is always pointing northward. That's why southward field is what matters when it comes to a solar storm, right? Because northward field will connect with southward field. If you have southward field coming in and northward field in the Earth's magnetic system, they annihilate each other, and it opens the Earth's magnetic system and allows all of that stuff from the solar storm to pump in, right? And then it energizes these current regions, okay? The stuff out in the very edge, right now, because remember the magnetic tail is this big long thing, as we call that the magnetotail. The current systems that are really out on the edge are what we call region 1 currents. These are the ones that come from the highest latitudes, the open part of the pole, all the way to the edge of the Earth's magnetic system. Outside here is open field. Right here at the edge is closed magnetic field. This is inside the system, but just barely. So it's going to be at the highest latitudes because it's at the highest L shell. Remember this? Just inward of that is going to be region 2 currents. They actually jump in at slightly lower latitudes. They're still in the pole, but they're slightly lower latitudes. Okay? They're slightly lower L shell, right? They're a little bit more protected. If we jump in a little bit further, you're going to get the ring current, right? Ring current is much more protected. And if you recall, the ring current, right, is much slower to respond because it's more protected. It's much slower to respond to storms, to magnetic disturbances, right? You always work from the outside in. When a solar storm hits the Earth's magnetic system, it always peels the highest L shells off first, folds that flux back into the tail. Remember from the magnetospheric lessons and even ionospheric, I talked about this over and over again. You guys should be like going, oh, yes, Tamitha, move on. Hopefully you are. So what we talked about last time in class is we really went over what we call the AE index, okay, which is really talking about the auroral electrojet. And the auroral electrojet, like I showed you in just the last slide, really sits kind of right in here, okay? It's just underneath the region 1, region 2 currents typically, but they're connected by that convection that we talked about just a moment ago, and also in the ionospheric classes, I talked about those gravity waves. I talked about some of that convection that occurs. And it actually, some of that convection actually occurs all the way down into terrestrial weather, right, into the neutral atmosphere, right? We have that, even that polar vortex that couples into the and the neutral, the flywheel. We talked about that, which we think was part of the reason why some of the Starlink satellites fell. So we do have coupling with that auroral electrojet which we have coupling in the sense that the auroral electrojet can sense some of the things that are going on with the region 1, region 2 currents, which is why it's good for aurora. And we'll talk more about that again. We also then talked at the very end of our class last time, we talked about the DST index, which is a measure of much lower latitude and is a measure of the ring current, right? And we talked about how slowly it begins to rise up. And why? It's because it's looking at L shells that are much more protected. So if I quickly go, okay, this is where I think I'll pick up, and I'm going to do these quickly again while my legs are on fire. But this is just to kind of reorient you. So I'm not going to go into this nearly as deeply as I had before, but this is to give you just a little bit of orientation. Now remember, we're talking about magnetometer stations. So what we're trying to do, what we want, is we're wanting to measure the wiggles, the amount of magnetic disturbance, right, down on the ground. And let me know if you need me to remind you of the coordinate system, okay? Because we're talking about the H, the D. Oh my goodness, what is going on? If people start calling me on Facebook, I'll be in real trouble. I'll have to turn that off. Sorry about that. The messenger is such a pernicious little device. At any rate, okay. So let me know if you need me to go over the HD, ZF, all of those coordinates again. Yeah, boy, today is a day of distractions, isn't it? I'm telling you. Hold on, I'm going to have to turn the phone on Do Not Disturb, sadly. There it is. Hold on, folks. I am a popular person today, and that does not make me happy. Not when people butt in like that. All right, sorry, Jerry. We're on Do Not Disturb. I will look for texts, but I will not get pinged because I had to turn it off. Do you guys need me to go through this again? Because this is the coordinate system that has to do with the magnetic field. When you're on the ground and you're looking at magnetometer data and you're looking, and you've got to get a coordinate system, right? Because the wiggles are happening all over the place. And really what we want to focus on is the horizontal component, which is really how the magnetic field, if it's coming straight into the Earth, because it's mainly vertical at that point, it wiggles back and forth, right? So you're wanting to know the deviation this way and this way, parallel to the Earth's ground. That's why the H component becomes the most important, even though you have a field component that actually is, at some oblique angle to the ground. We really, really care about the H component. And then anything in this plane, the X and the Y component, really are deviating from, are the H component that you add up together, but they're deviating from true north. Okay, so it's really just a matter of which direction are you pointing relative to true north, but that's still horizontal to the ground. Okay. So anything else, we talk about declination and inclination angle. We're talking about angles that typically are well, not the declination, but the inclination angle is the angle that is non-horizontal. It tells you how tilted toward the ground it is. The declination angle is basically the difference from where you are to true north. Okay, so that's a little bit of a review. If you need more of a review than that, please go back to my previous mini course on this, on the ground effects. And let me get back to here. So we will look a little bit at, if you look at magnetometer data specifically, you will need to know those that coordinate system. However, one thing we've often done, as you'll see in a minute, is that we have translated that data into indices, which make it much, much easier for non-experts to look at, and also gives, kind of bins the data so that even scientists and climatologists can actually go back. Space weather scientists and space climatologists can go back and look at historical, data and not have to dig straight into the magnetometer data. They can actually characterize things by these indices, which gives us kind of I don't want to say a quick and dirty, but oftentimes that's really the only level of detail that we need if we're going through and doing a huge statistical study. We don't always need to see the minutia. And so indices are a way of getting a lot of information very quickly without getting lost in the minutia. So just be aware of that when we talk about these indices, oftentimes you will see these indices given as numbers instead of, even though all of these are magnetometer stations that do give real data, right, in the coordinate system that I told you about. So really the devil is in the details when it comes to the kind of information you can gain from magnetometer stations. But for space weather enthusiasts and people who are looking for aurora and people who want to do auroral propagation, or just want to understand what's going on with our local magnetic system, indices are fine. They're completely fine to use as long as you know how to use them. So starting at the highest latitudes, again, here is the magnetometer chain that is responsible for what we call the auroral electrojet, or what we call the AE set of indices. Now, AE is only one of four, right? We've got the AE, the AU, AL, and AO. I'm not going to go into them in too much detail. just know that AE is kind of a summation of the whole thing. It shows, it kind of bounds the both the upper and the lower index, the auroral upper and the auroral lower. We're talking about the eastward and westward electrojets. These are the things that are occurring just in and around this magnetometer chain below the auroral oval. Okay. Now, because it's at high latitude, that means high L shell. That means it's going to be basically on the front lines of space weather, right? The higher L shell you have, the more susceptible it is to incoming storms. Okay. So you can imagine the AE index is going to be, as you see, at high latitudes, right? It's going to be L5, L of 6, L of 7, right? So you're talking geosynchronous and beyond. You're talking out in here, okay? You're talking getting really close to the outside where the field-aligned current systems are, outside of the ring current. So we're not picking up the ring current at all, okay? So this system is going to be extremely sensitive to aurora. And sure enough, and extremely sensitive to substorms, okay? Sure enough, when you look at Kyoto, for example, right, here is a reasonably recent solar storm, the 26th through the 28th of September. And remember, I'm still going over this quickly. If you want a deeper discussion of this data, you can go back to the prior mini course. You have the upper index, which is the top line, the lower index, which is the bottom line, and you can see the difference. What we oftentimes do when we look at these indices is that we want to see the difference between the two, right? How radically different is the upper to the lower index. And that is what we see in the AE index, okay? So when you see the AE index going over 500, you're going to be getting substorms. Okay, that's kind of a rule of thumb. And I talked about this last time. So here is a very good brightening. And as you can see, over this time period is in universal time. This is 1 day. Okay, this is just the 26th of September in 2020. And it wasn't really a super strong storm. And I think I'll show you in KP in a short bit. We'll compare these indices. So you can see the difference between the AE suite and KP. And you can see the difference in the sensitivity and therefore how they're used. Okay, so the AE is going to show you the bounds, basically, and anything over about 500 is going to be, if you're especially at high latitudes, it should tell you, yes, substorms are happening, and yes, if you're a satellite operator, it should also tell you that yes, surface charging is happening. So satellite operators can also use the AE index if they're savvy, and it typically means substorms are happening, spacecraft charging is happening in the post-midnight to pre-dawn sector, and it'll be sporadic. Okay. The AO index, just for comprehensive, completeness, the AO index is an average. It's just essentially the average. It's the upper index plus a lower index divided by 2. Okay, so you're getting a lower bound here of the average. Yeah, I'm going to leave it at that. So again, you can see there's a lot of detail, right? You can see when the aurora brightens, like in here. You can see when the aurora dims, like in here, and then it brightens again. These are definitely substorms, okay? Not a full-blown geomagnetic storm, right? A full-blown geomagnetic storm affects the ring current. That's when the flux is peeled down further and further and further, getting bitten, peeled down further and further and further to lower L shells. And I'm going to be a mess by the time this is over. Goodness, this is a hungry mosquito. Okay. And where was I? So when you see this in a real geomagnetic storm, you're not going to see just little bursts like this and then quiet and then burst and then quiet. You're going to see just, it's going to look crazy. And here's another day of this. So you can see for a while, what you can see in this particular storm is that we had some bursts of substorms and then things would quiet down. In fact, when we went to the 27th, things quieted down almost for a full day. I mean, we're barely getting any substorming at this point here. Things quiet way down. And then, as you can see, things begin to pop up again. The colors have everything to do in this case. Kyoto is wonderful. They tell you how many stations are reporting in. There are 12 or 13 stations in the AE index suite. And so it doesn't tell you how strong something is. It's only telling you how many stations have reported in and how much data has been get. So it gives you kind of a quality flag on whether A, the data is going to change, and B, how much you can rely on it. Okay. Because remember, all of those stations, and I don't think I said this last time, it's crucial to remember all of these stations are at different local time, right? They're all around the globe. And so if you're on the day side and you're the magnetometer station, in the AE index, well, you're probably not going to report nearly as much activity. You might, but there's a lot of other stuff going on the day side. You're not peeling, when you peel the flux back, oftentimes you're peeling it back and it goes to the night side. If you guys remember from how we actually peel flux back from the Earth's magnetic system, it peels back to the night side, and then you get a lot of particles that are shooting forward from the night side. So there's a lot more wiggling going on in the night side. And so if you're a magnetometer station and you're on the day side and you're one of the first magnetometer stations to send data to Kyoto to try to make up the AE index, well, then you may be underrepresenting the amount of activity that's actually going on. Or if you're a night side station, you may be overrepresenting the amount of activity going on. So that's something that you have to realize, that when you look at this data and you only have maybe 2 or 3 stations reporting in, which I rarely see. I think the lowest I typically see is around 3 to 4. That's when you really kind of have to pay attention and go, well, okay, well, wait a minute. let's not take this too seriously, because I don't know if it's day, if it's on the day or the night side, which stations are reporting in yet. Okay, so just keep that, take that with a grain of salt. And then here again, but once you get about 4 or 5, maybe 6 stations, you're like, okay, this is getting pretty representative of what's going on around the globe. And then here's the 28th. So these are now 3 days, 1, 2, 3, 26th, 27th, and 28th. And as you can see, we had some substorming going on, boom, boom, boom. But then you just kind of start seeing it when it begins to just all kind of fit together, and it's just never turning off. Yeah, you're pretty much in a geomagnetic storm. And likely KP at this point lights up. Okay. KP might have lit up a little bit here and there, but it won't be nearly as dramatic as this. Now, we'll talk about KP in a sec. Let me recall, because now I went into DST. And I don't want to spend too much time on DST because I want to get to the comparisons. Okay. Whoops. You silly thing. Go like this. Okay. So I'm going to move through this a little bit faster. So the DST index, as you can see, now we're talking about the ring current. Okay. So we've moved way in to the inner part of the Earth's magnetic system. We're in protected or unprotected L shells now. So we're not going to see the front lines if we're looking at DST. DST, as you can see, is much lower latitudes. There's only 4 stations, and there's lots of reasons for that. Okay, DST is a long index. It's been around since 1957, and it's, as you can see, much lower latitudes, right? And really, what we're trying to measure, and as you can see, it's both in the north and in the south. Unlike the AE index, which was all in the north, and we expected basically there to be the conjugate aspect, that when what happens in the north in the auroral oval happens in the south in the auroral oval. That has to do with conjugacy. That has everything to do with the fact that Earth's magnetic system, right? You have magnetic field lines that come out and loop back down. So what happens up here will also wiggle down here. So you don't necessarily have to have magnetometer stations down here if you have magnetometer stations up here, because you can pretty much, they kind of mirror each other. Okay. But when you're in the ring current, you kind of want to have as much as you can possibly have. You want to be able to measure the ring current both in the north and the south, right? Ring current really is the energy storage of the Earth's magnetic system. It's not all the mass storage. The mass storage actually happens in the ionosphere, but the energy storage is in the ring current. And this means that it's slow to wind up. Takes a lot. Remember, the ring current is literally, and I have to go over lots of stuff, right? You've got the 3 adiabatic invariants, or if you have to talk about the particles are actually bouncing from pole to pole, right? They're also, they're gyrating, so they're gyrating around the magnetic field, they're bouncing, and they're drifting. And as they drift, they create the current, okay? So it's kind of a smear, granted, but when you average out the bounce motion, right, because you go up and you go down, they kind of cancel out each other, you get a current essentially that lays in the ecliptic or in the equatorial plane, okay? So we're able to talk about that ring current. It's much, if you recall where the ring current essentially sits, it's in and around L of 4 down to about L of 2, right? It's kind of smeared out, but it's much, much closer to Earth than, let's say, the field line currents are way out here at L of 5, L of 6, L of 7, and possibly beyond if those field lines aren't open. And so what we care about are L shells down in here, right? So L of 1, L of 2, L of 3, right in here, okay? And that's why you see the magnetometer stations where they are. If you have a lot of magnetometer stations, the more magnetometer stations you have, the harder it is to keep the index up. And I'm sure magnetometer, historians of DST know a heck of a lot more about it. If you go to Potsdam, for example, you can really get a lot of information about why historically these stations are used, how long they've been around, and why we don't change them. But we do have backups for DST. I think there's 2 or 3 of them, which I think I talked about last time. Oh yeah, look. Speaking of, here are the ones that are working right now, and they also create an index, the ASY index and the SIM-H index. These are other indices which I might actually talk about. I'm going to skip this time. We talked about this last time. The SIM-H index is a faster cadence, higher resolution, higher time cadence. We'll talk about why this type of thing comes up. We'll talk about that very shortly when we talk about the HPO indices. Basically, the SIM-H index is a high resolution, high time resolution version of DST, which is only hourly. Okay, remember, we have to keep these things the same because historically they need to be the same. But we realize now especially that we need much higher time cadences, and we're capable of doing that. But we can't change DST, otherwise it would render it impossible to look at historical and compare directly with historical events. So we have to create new indices. Okay, but they're very, very compatible. Obviously, they're using the same magnetometer stations. But there are some differences. And I talked about that last time. They're not huge, but they're bigger. The differences get bigger for bigger storms. It's kind of an interesting thing. But if you're interested in that, you can take a look at for example, at Wanless's paper here. Okay, Wanless and Showalter. I also went over the DST index. It is a negative index. And the reason why it's negative is because you're depressing the magnetic field. When you have the ring current, the magnetic field has a dipole moment to it, and it's pointing north. But the ring current works in such a fashion that as it intensifies, it actually induces a magnetic field direction that depresses, opposite of our magnetic moment. And so it actually depresses, when it's energized, it actually depresses the Earth's magnetic field strength. And that's what we're measuring here, is depression of the Earth's magnetic field strength in nanotesla. So it's always a negative index. Okay, small storms are sitting less than 100, about minus 50, less than that. Big storms are about minus 300. When you get up over here, holy merd, you're talking about, KP9, even beyond. Okay, we're talking about major events. Very rare for us to see a DST of minus 300. It does happen though. As a matter of fact, Carrington class event, some of the reconstructions show DST over 1,000, minus 1,000, right? Scary. Here's an example of DST for a storm back in that same storm. September 26th through 28th, we just looked at for AE index, where the AE index was kind of wiggling and you saw a lot of detail. Not so much with DST. I mean, it's just not even, it's like hardly minus 50, barely makes storm level, if it is even storm level. Okay. Here's SimH, much higher resolution. You think, oh, well, the high resolution makes a big difference. Yeah, okay, maybe, right? Here's now September 26th, 27th, 28th. You still don't see the resolution that you saw in AE. You know, it's not nearly as high resolution, and it's not nearly as responsive as the AE index suite of indices is. And that makes sense, right? This is a protected L shell. We're at much lower L shells. We're in the heart of the Earth's magnetic system. We're not at the fringe, right? So we're not on the front lines. Okay, so that's the end of the review. I think that was the end of the review. I think because we're going to go into the KP index now, right? I don't think I did KP last time. Maybe I did a little bit. No, I don't think I did. 32, right? Yeah, I didn't. Slide 32. Sorry, guys, COVID brain still kind of that and the mosquito. Oh, sorry. So I'll pause here for just a second. I know this isn't my most organized mini course. I'll apologize for that. To see how did you guys get all that review? Was that okay? All hail Tamitha. Oh, thank you. That's so sweet. Hi, Lisa. Good to see you here. Let me know, guys. Hey, Metal Halo, I have a natural version of off, and I used it. As a matter of fact, the sprayer wasn't working, so I pulled it out and poured it on my legs. And this thing is still after me. So it didn't work at all. I don't know why. I'm not really sure why. But yes, I did do off, and it didn't help. Okay. Hi, Lisa. She's reviewing still. Okay, good. Yeah. Alan, get some E45 cream if keep getting bitten. E45, what is that? I don't even know what that is. I'll look for it. I'm going to write that down. Wait, do I have a pen? Do I have a pen nearby? Yes, I do. I'm sure I do. Hold on one sec. I am always looking for better mosquito, help, repellents, because I don't have much that ever works. E45 cream. I'm going to write that down, if that's a real thing. If you're not just joshing me. Oh, that's sweet. Thank you. You just now smashed the like button. That's nice. Okay. No worries about being late. I just did the review. We've just finished it. It's because it's been so long, right? It's been several months since I've done a course for you all. I really wanted to be able to review, and I know it was kind of scatterbrained, but I'm doing the best I can. Okay. Did I see your question? I don't know if I saw your question. You're not even asking that of me. Okay, good. Review helped a lot. Thank you, Wild Spirit. I appreciate that. And I shortened your name. I hope you're okay. Yeah, Marilyn, don't worry if you're not educated in this. This isn't a reasonably advanced class at this point. But I tried to kind of soften the blow a little bit. Even if you go back to the class just prior to this, which I think I did on May 8th, it's E1 is the label for it. This class is kind of picking up where that one left off. And so even if you watch that class, you'll actually get a better feel for what I'm talking about here, because everything I just went over, I went over very quickly. And so if you feel a little bit lost because I'm not explaining things well enough, understandable. My reviews are usually pretty quick. And I think I took a little bit more time than I normally do, but still, it's unless you are familiar a little bit with the material that I talked about last time, you may not, it may go over your head. And yeah, I'm glad the review is helping a lot of people. Hi from South Africa. Good. Hi to see you. Glad you're here. Bactine is good for bites. Yes, I'm going to put some on after this class. Hairspray. Really? Because I have some hairspray. Does that really work? Wow. I've never thought of that. The effect is neutralized. I know, you know what? I almost brought alcohol in here, strangely enough. Okay. I'll stop talking about the mosquitoes because that's really kind of off topic, isn't it? Solar activity and magnetic activity. What's the difference, please, in layman's terms? Oh my Lord. The thing is, solar activity and our sun is dominated by its magnetic field. And I'm slightly biased. I grew up at UCLA, cut my teeth with Chris Russell, and so magnetic fields are dominate to me. just because they're not necessarily the easiest to visualize, but they play by the nicest rules. Electric fields are oftentimes very chaotic and stochastic, whereas magnetic fields have to open and close and do things that are that make more sense. They're much like, in a sense, much like slinkies. Magnetic fields are very springy, and they have, this kind of thing you can kind of visualize. Even if you can't see magnetic fields, you can actually visualize this type of thing quite easily. I use the slinky so many times because there's so many different areas where this particular shape really indicates, really dominates a lot of the phenomena that occur, even in the sun, because the sun has a dipole field just like the Earth has a dipole field. And when the sun launches solar storms, believe it or not, the solar storms are filled with this, and they're filled almost looking like this. They have what we call a flux rope structure in them, where they look very much like this. And I talk about that all in my coronal mass ejection, solar flare. I talk about that in the early set of mini courses that I do. And the reason why the magnetic field is so unbelievably important is the same phenomena that you feel and that you discover when you are playing with fridge magnets, right? If you put two fridge magnets together that are the same polarity, they repel each other, and you can feel them repelling, almost as if there were a spring in between them, right? You can feel that repulsion. But if you flip one over, they suddenly click. And that really is the key to space weather when it comes at least to how it interacts with Earth and other magnetized planets. Remember, Earth has a magnetic shield. So if you look at Earth being a fridge magnet, and you look at the sun sending solar storms, which are also like fridge magnets, they either will bounce off each other like bumper cars, or they'll click. And if they click, what happens is that what was once a single magnetic system, and you have two of them, suddenly they reconfigure and they become a single magnetic system. So now the Earth, in that case, the Earth's magnetic shield is not only dealing with its own stuff inside its shield, it now has all of that stuff from that solar storm being pumped into it, okay? Because now that all that stuff that was previously, apart, separate, is now connected, and it can freely, energize and pump all the particles and all the current and all the mass right into the Earth system. So when we talk about the sun, we do talk about its solar, its magnetic field. Its magnetic field dominates so much of it, not just space weather. It dominates actually the solar cycle, for example. That's all about the sun's magnetic field and how it flips like a lava lamp, which is honestly part of what Earth is doing right now. Earth kind of does the same thing, just on a much longer time scale. That's why people are talking about the Earth's magnetic shield flipping. They talk about it going away, but it's not really doing that. It's just reversing. But the sun does that every 11 years, and it's the magnetic field that's reversing. And because the magnetic field of the sun dominates not just the sun's orientation and the sun's polarity, but dominates, and not just the sun's cycle, but also dominates the transients that come off, the solar storms that come off. It plays such a critical role in everything that is space weather and heliophysics, for that matter, and honestly, astrophysics as well. So much of the work that they do in astrophysics is all about magnetic fields and electric fields, and how they're kind of like brethren. They shake hands. If the left hand is the magnetic field, the right hand is the electric field, and vice versa. You can't really have one without the other. And so really it will dominate from beginning to end everything I talk about in space weather. The thing about space and how space works is that it's not a vacuum. It's vacuous enough that the particles that we're used to, like in the air, that are collisional and bang into each other, out in space, those particles don't bang into each other. They can't. They're too spread apart. And so, in fact, really, you get about one collision in space, and in our solar system, you get about one collision. The particles will travel literally for the distance from the sun to the Earth by the time you get one collision. They collide once with one other particle. So we call that the mean free path. And it's about the distance from the sun to the Earth. That's how vacuous space is. But that being said, that doesn't mean the particles don't know each other exist. The particles are connected to each other through electric and magnetic fields. And these electric and magnetic fields act like a spider web. So that spider web then dictates, if you shake the spider web over here and that from that particle over here, it actually wiggles that whole web and a particle over here shakes. So from that point of view, even though they're not colliding with one another, they're interacting with one another, mainly through the electric and magnetic fields. So that's why it plays such an incredible role from sun all the way to mud. And that's why on the ground, we measure the magnetic field. And that's what the indices are based on. Because it's just, you can't do space weather and understand heliophysics without it. You just can't. So hopefully that answers that question. I'm sure that was a long-winded question, or long-winded answer, but these two, oh, this is fascinating. Okay, good. I'm always lost. I hope not, John. Don't say that. That makes me feel like I failed you. Getting educated for the Aurora Summit. Yes, wonderful. Good to hear that. I'll see you there. Okay. So mixed tea tree oil and alcohol. I will, oh, interesting. Tea tree oil. Okay, I'm gonna write that down. So tea tree oil and alcohol. Yeah, that'd be great if I could find something that pushed them, just repelled them. Okay, I'm glad you do this. I want people to get this as we need it for our young people. Yes. Oh yeah, did you see what was called the Northern Lights? Yeah, they are on year 78 now. Wow. Yes. That's what we're talking about. This is to a great degree what people are going to, why you use these indices. And we're about to get into the index that is sadly been used far too much for aurora, and this is why nobody sees it. This is why people believe the KP index, honestly, is, I would say, the sole reason why people think aurora, you have to go to Alaska to see it, or Iceland, or Norway to see aurora, when in actuality it's clear down into the United States. It's up into the Victoria, Australia, like a lot, far more than anyone ever realized. And we'll talk about exactly why that is in just a sec as I jump forward. Gotta love the solar slinky. Yeah. Our sun has several magnetic poles, right? Yes, the sun has two magnetic poles typically, especially during solar minimum. You always know that because you can actually see where the coronal holes are. The polar coronal holes, especially at solar minimum, are well formed, and they're both in the north and the south. As our sun begins to flip, its dipole field component flips, which means it goes to zero first before it reverses and gets strong again. That means that the smaller components of the Earth's or the sun's magnetic field show up, and those field components are actually multipolar. You have the dipole component, which is 2 poles, the quadrupolar component, which is smaller, that has 4 poles, the octopole component, which is smaller still, has 8 poles, and so on and so on and so on. And so as the dipole field reverses and goes to zero, it exposes the quadrupolar component, the octopole component. And so suddenly you have, instead of 2 poles, you have 4 or 6, or good night, you have a lava lamp, which is what I call it. And you can see that very well by looking at what the coronal holes are doing. So for example, if you look at the coronal holes right now, you're not seeing what you saw back in 2019. Now you're seeing little mini coronal holes like all over the place, right? We've got two coronal holes. One was in the north and in the south, but then we also have 2 coronal holes that are like mid-latitudes. Well, the reason for that is that that field is beginning to flip and the dipole field is weakening. And so we're getting a much more strong influence from those weaker components of the sun's magnetic field, which are the quadrupolar and the octopolar and so on. And you'll see that. So when we get to solar maximum, the sun will be a mess. That's why I call it a lava lamp, is because if you ever turn a lava lamp on, before it looks nice at the beginning, you got the clear liquid and the thick stuff, right, separated quite well. That's kind of like a North Pole and a South Pole. But then as it heats up, boy, all you start seeing are bubbles pretty soon. And pretty soon it's a mess of bubbles. It's like, what the heck, right? And that's solar maximum. And then if you turn the lava lamp off, then it cools down and everything separates out again. And you're back to solar minimum. So it's kind of like a lava lamp turning on and off, right? And you look at it as those being like, in a sense, magnetic islands in that lava lamp. And that's kind of an easy way to think about it. But that's really what's happening. And the Earth's magnetic field does it too. It just does it on a much smaller or much slower time scale. So nobody should be worried about the Earth's magnetic field flipping over. It's not a problem. We've done it before, and the sun shows us how every 11 years. So it should be just fine. Okay, So one more thing I see, someone pinged my name, are the electric and current waves at right angles to each other in solar weather? No, no, no. You can actually have electric fields and magnetic fields being parallel. We call that's actually one of the things that happens in aurora. For example, you get an electric field that's parallel to the magnetic field, and it accelerates particles down into, because the fields, you have field aligned currents, for example, that should kind of dictate, should kind of reveal that. If you go to the ionospheric courses that I did, you'll see that. We talk very extensively about that. And you accelerate particles down into, especially electrons, because they move much more quickly. You accelerate them down into the upper atmosphere, which then allows them to light up the atmosphere like a big neon beer sign. So yeah, I talk a lot about that, and it's not, the polarization isn't the same. They don't work like it does in RF fields, although there are wave processes that are very much like that, and there's a whole discipline of space physics in which we actually study waves. I mean, that's one of the reasons why people have antennas out on the spacecraft. And radio bursts is a classic discussion of them. Kilometric radiation that we have all in the Earth's magnetic system in near Earth space is an example of that. There's all sorts of things, EMIC waves and chorus waves and AKR and magnetospheric hiss. I mean, there's just so many different names. And if you go back to the magnetospheric courses, I'll talk a little bit about those. But there's a lot of, that's just one aspect of the phenomena that occur during, let's say, during a geomagnetic storm, and otherwise, sometimes even during substorms. That's not what I'm focusing on here. I'm not going to focus on pulsations, and because there's a whole bunch of different types. But yes, you can see them in the magnetometer data. There's regular pulsations as well as continuous pulsations as well as irregular pulsations, and there's all sorts of different types of them. If you're interested, look up PC 2, 3, 4, 5, or PI. PI stands for irregular pulsations or regular. PC is pulsations continuous. There's a whole field that's all about that. And if you're an amateur radio operators, those might actually intrigue you quite a bit. They also might intrigue you quite a bit if you have sensitivities. Like some people are sensitive to electromagnetic fields, and it bothers their health. It'd be very interesting to see studies that are done looking at pulsations, both the continuous and the irregular pulsations, because there may be something there. Anyway, that's a story for a different time. Okay, guys, hopefully I answered enough questions so that we can move on to the new stuff. Okay, so getting to the KP index. Now, we just talked about the auroral electrojet indices, right? Being very high latitude, being high L shell, being an index that kind of shows you what the soldiers on the front lines are doing, right? If you think of it as like a chess game, the AE indices are talking about the pawns, right? They get to see what is being, who's being sacrificed, right? These are the soldiers in the trenches. And then we talk about the ring current and DST. And the DST is the index that really is talking about the back, the very back row on the chess game, the chessboard. You're talking about the king and the queen and the bishops, right? You're talking about the ones that are kind of held back a bit and are well protected. So that's what the DST index talks about. So only if a storm is really big and really penetrating your defenses is DST going to really start registering. But just at the slightest hint of a conflagration, of a fight, of a solar storm impending on the Earth's magnetic system, AE index will light up quite readily. So you can imagine, just like a chess game, that a very powerful storm from the sun, if it's the opposite chess player in this game, and it sends out a queen to confront your pawn, your pawn is going to get overwhelmed quite quickly, right? Because something strong coming from the sun is going to knock that pawn out very, 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 very fast. And that's what ends up happening with the AE index, is that it gets overwhelmed, right? But when you think about these indices, you can think, okay, well, the DST index isn't sensitive enough to small storms. It's only really sensitive to the big storms, but the AE index is so sensitive that it gets overwhelmed so quickly. Well, what do we do about that? What about a mid-latitude kind of thing? Because think about it, United States, a lot of people live in the United States. We don't all live in Canada, or New Zealand. And so we want that. We want to be able to have a mid-latitude index. And besides, it's really easy to install magnetometers, mid-latitudes, right? So don't you think a mid-latitude set of magnetometers might kind of feel a little bit of both? Well, there you go. This is what the KP index is, okay? And this is one of the reasons why the KP index is such a great index, to kind of get an overall feel of the global system of Earth. In fact, the whole planet, right, getting an overall feel of how the planet is doing is actually part of the KP name. P stands for planetary, okay? It's supposed to be global. That's the whole thing, which is both a blessing and a curse. And you can kind of start seeing why here really quickly. If you had just a K index, and we will talk about K indices, right, because there is such a thing, lowercase k typically, they're local indices, right? They're going to be the K at one or multiple locations in mid-latitudes. But if you get the planetary index, well, basically you're trying to kind of gauge what's going on all around the globe at around mid-latitudes. But when you think about this set of indices, or this index rather, and the set of magnetometers, well, you're already kind of averaging a little bit of what's going on at high latitudes, at high L shells in the AE index, and you're also not completely isolated from what's going on in the ring current, right? Because ring current actually around 40 degrees geographic latitude is about where the highest magnetometer stations are for the ring current, okay? So you're getting a little ring current influence from low L shells, and you're getting a little bit of auroral electrojet influence from high latitudes. So it's already kind of smeared out in terms of what it is that affects KP, right? And now you're going to do it globally. You're also going to get it in all what we call all local times, right? Remember, because we have day side and night side, and they get affected a bit differently. Things aren't completely symmetric. And it's because the Earth's magnetic system isn't symmetric. Notice we do have some stations in the south, right, at mid-latitudes. We do have stations, obviously, focused mainly in the north. And yes, there's a bit of conjugacy. Again, we have to rely on that. But remember, there's a lot more landmass up here in the northern hemisphere than there is in the southern hemisphere. That's easy at these latitudes, right? I mean, look at 40 degrees south. I mean, we just almost all ocean down here, right? So we have to kind of make do with a lot more stuff at high latitudes. But we do try to get the spread in local time. So that's why we have things in Australia and New Zealand. And we have things, of course, all the way to Alaska. And this is one of the longest enduring indices, right, from 1932 onwards. It's not the longest. I think the AA index is probably the longest, made up of like 2 stations, I think. And it's one of the ones that we do most of the climatology with. But from 1932, that's pretty good, okay? Now, it's a 3-hour interval, so it's averaged. And now notice I'm going into a bit more detail because I'm not reviewing anymore. So if you notice, this is a pretty rough cadence, time cadence. And if you're trying to chase aurora, would you want to have a forecast only every 3 hours? I don't know about you, but I don't think I would. How about, let's make it a little bit worse. Let's say it's not a forecast. Let's say that 3 hours basically sums up what happened in 3 hours ago. Would you want to know about aurora 3 hours late? Probably not, right? Because this is what happens. Typically, KP index jumps, and everybody goes out looking for aurora. But the aurora is already dying down, or the aurora is already gone. The aurora already happened 3 hours ago. People who chase aurora using the KP index are going to be disappointed almost every time, especially when it comes to smaller solar storms. And the reason for that is because small solar storms don't last all that long, or Small solar storms are more sporadic in their aurora display. The only time you get really good aurora, forecasting from KP index is when the storms are massive. Well, it doesn't happen all that often, right? So it's just not the best. Not to mention, it's not getting AE, it's getting AE and ring current. So it's kind of a smear in that sense. And so it's less sensitive than AE might be, or AE is rather. And so not only are you getting the data not really in real time, but you're getting 3 hours in the past presented as now, not good. And it's already kind of dumbed down, so to speak, in terms of things like wanting to know exactly where aurora is and when it's happening. So it's nice, it's useful in some ways. It's useful for certain scientific things, it's useful for historical things, it's useful on a planetary scale to get an overall feel, but of larger storms, medium to large storms, okay? And yet we use it for everything, sadly, okay? In fact, we don't just use KP, we derive tons of other indices from KP. And I'm not even going to talk about all the details of all these different indices. Okay, the one that you guys are probably the most familiar with if you're an amateur radio operator are the AP indices. Okay, and I'm going to say something that may be considered completely revolutionary and blasphemous to those who have grown up cutting your teeth on the A index. It's useless for amateur radio. It's useless if you want to do climatology, meaning just like terrestrial weather, we have climatology where you're looking over months, if not years of data, right, to get. How long was I out? 20 minutes. I pulled that one time and you know what, I'll turn my phone back on. Hopefully the jerk on who made me go put my phone on do not disturb is gone. You guys have to tell me how long I was out. What slide was I on? Anybody remember? 12:20. Wait, what does it say? 12:23? What time is it now? Oh, not too bad. Couple minutes? Check, check. Since I spoke about 4 minutes? Really? Yikes. So I was still on this slide? From AP is no good. Okay. Oh, good. Just 2 minutes. Oh, thank goodness. Yes. The the spamming the chat with all the red stuff. Oh, that got me. Thank you. Thank you. Oh, you saved me, guys. For any of you who remember, I don't remember. It was like 2019 or something. I think there was 17 minutes of no audio in one of my courses early on. That course is still available. It's still up. I don't remember the course, which one it was, but I think it was 17 minutes. Oh my Lord. That was what got me to always make sure my phone is on. And see, that's what happens. Yes, Keith, I see you. Mike, yes, I see. This is why I can't put my phone on Do Not Disturb. So when people call me on Messenger or something like that, it drives me nuts because, whew, okay, not so bad. Oh, this has been a hilarious mini course, hasn't it? I'm so glad you guys have a good sense of humor. Okay. For amateur radio, A index is useless. For climatology, and then that was it. Thank you, James. I appreciate that. Okay. Oh, Adrian remembers that one. Yeah. Oh, man. That was a funny course way back when, right? Okay, so I have, I think these are the warm ones. Okay, so these are dead. Let's hope I can continue surviving. If these go out, I'll be much more on it, but I don't know if these batteries that I have, if any of them are any good. So if I go out again, just spam the chat again. My daughter used all my batteries. So I realized I started this course and I said, uh-oh, I don't have any brand new batteries. Oh no. So yeah, anyway, okay. So what I was saying was that the AP index is no good. So we were talking about the A index and all of the other indices that are derived from the KP index. But here's the thing with the AP index and the A index in general, and this is where I think, yeah, the dog ate my homework. This is where the A index fails in general, is that if you're doing climatology, if you're doing something where akin to terrestrial climatology, you're looking at things over months and seasons, if not years or even decades. That's great. The A index, have at it. It's perfect, right? But if you're someone who is an amateur radio operator and you're sitting, let's say here, right, and you're looking at propagation, you're looking at the propagation for today, what you want, on 20 meters. I don't know. Let's just make something up here, and you want to know what the space weather conditions are going to be like. Well, here's the problem. The A index gives you one day, or gives you 1 point. Okay, one data point for an entire day, and it's the average of the KP index for that day. Not the average. Yeah, it's the average of the KP index for that day. Okay, so you're already taking an index. This is an index that's already time averaged and limited in time. And it's already limited from the sense that it's got part of the ring current influence and it's got part of the AE, the high latitude influence. So you're basically smearing together. You're smearing high latitudes at high L shells, L of 6, L of 7, and beyond. You're smearing that all the way down to low L shells, L of 2, L of 1. Okay, 1.5. Right? You're smearing all of that out so that you're not really getting the high sensitivity for just aurora out on the front lines. You're getting also what's going on in the heart of the Earth's magnetic system. So you're already kind of dropping the sensitivity down, and you're smearing it out in time, and you're smearing it out in local time as well, right? Because some of these stations are on the day side while others are on the night side, because this is supposed to be a planetary measurement. And now you're going to average that so that you get 1 point for the entire day. How is that supposed to help somebody who's sitting over here, in Wisconsin, wanting to know whether or not 20 meters is going to work? It's not. And this is why amateur radio operators who have cut their teeth on the A indices say, I don't understand how these indices work, right? It's not that there's something wrong with the indices. The indices are designed in a particular way. The problem is that space weather is still a field. It's basically where terrestrial weather was back in the 1950s. And so it's very difficult to use any of the data products that are made for space weather without a scientist in the loop. Okay, these indices are very good indices, but they're used for very specific things. And if it's not clear how to use them or what they should be used for, then the non-expert is going to say, well, space weather makes no sense and I can't figure it out. And they're either going to blame the scientists for being horrible at their job, or they're going to blame themselves for being impossible to teach. And that's not the way it is at all. Neither is true, right? It's just that you're using the wrong index. There is no hope of trying to make sense of radio propagation using A, unless you're trying to understand long-term trends over the solar cycle. Then A index might work, right? But if you're trying to get a daily propagation report, don't just laugh at A anytime you see it. It's a joke. It's not useful, okay? To a great degree, KP isn't even useful unless it's a really big storm that's long-lasting. It's not useful, right? It'll tell you what happened in the past. It's not going to tell you what happens in the future. Local K, right, which are now independent stations, the magnetometer data from these independent stations turned into K, turned into a K index, much better, okay? Because that at least gives you locality. And obviously the best will be straight magnetometer data, but who necessarily wants to read that? Unless you're a scientist, then you can get stuck in the minutia. Now you got to understand coordinate systems, you got to understand what you're looking at, you got to know where to get the data, you got to know how it's calibrated, right? I mean, granted, all of them follow, if you guys remember from the last course, we talked about all of the quiet systems, quiet current systems that are backed out of all this data, right? And we even talk about this, I believe, here. Yeah, standardization tables created by Bartels, and we'll go into Bartels a little bit more. I'll show you some fun stuff in a minute. And they remove, seasonal variations, the daily variations, the SQ, the quiet, solar quiet, that type of thing, the lunar tides, all that stuff, all the stuff that we talked about back in the previous course. So the K index is a wonderful index if you want to look at things that really are planetary to a great degree, because you're smearing out your L shells, right? You're going from high L shell to low L shell. So you're getting kind of a feel for what is going on in the Earth's magnetic system in a global sense, and you're smearing out over all local times. So it's a nice index, really, to kind of like, I hate to say this, but it's a nice index to kind of say, is there a big, is there something significantly disturbing the Earth's magnetic system or not? And basically, it's a good alert. If you're a satellite operator, for example, it's a good alert to say, okay, there's probably no orbit that any of my birds are in that is going to be not impacted, right? Means if KP lights up, then that means you could be impacted in Leo. It means, because you could get the inflation of the atmosphere. Okay. If you and that's important for for Starlink, for Blue Origin, for all these Leo birds that have to deal with drag. It also is an issue for the ISS and for human spaceflight, right? Because when the KP index lights up, it means, oh my goodness, surface charging could be an issue, and you do not want to do an EVA when there's a significant activity, because the poor astronauts, they act as Langmuir probes. They can actually get shocked pretty badly, and that is very dangerous when they're out in EVA. So you won't have EVAs typically when KP index is high. And that's once again in low Earth orbit. In middle Earth orbit, MEO, you have transient problems. You have a lot of particles, a lot of flux being dumped into the system. And if anybody tries to fly in the slot, so to speak, the slot's gone. So that indicates problems in MEO. And if you're in GEO, problems again. You're likely getting surface charging issues because you're getting the radiation belts being pumped up. So it's kind of like a nice thermometer or barometer for the entire system to say, yeah, we've got problems, right? But it doesn't have to be a huge geomagnetic storm like what you would get with DST, and it isn't just a teeny little wiggly guy, little substorm like what you get for that causes local problems, like what you see in the AE index. So that is why KP index kind of is the go-to index for a lot of NOAA and NASA, work, right? Especially the operational side of things, because they're the ones that have to like make sure that the power grid companies are savvy and know what's going on. The satellite operators are savvy and they know what's going on. And the aviation industry is savvy and they know what's going on, right? And so this is a really good barometer. But using it to chase aurora, using it for amateur radio, not so good, right? Because we have much better tools for those types of things. So hopefully that clarifies that to some degree. Slight buffer. Oh, wait. Am I still okay? Okay, good. Okay. I'm just checking to see if I'm having, if everything is clear. You guys, does that make sense? Oh, I will talk a little bit about, when I start showing the KP index, I'll talk a little bit about the levels, in case for those of you who are not familiar at all with the levels of KP, to talk about, and also how things are changing. I probably should bring that up. There's the Space Weather Prediction Center is changing their coloration to align more with their scales. So I might mention that. Okay, so again, we've seen this many times, but this is now the K magnetometer stations, right? You see them here kind of in this band, which really is showing you that it's a band kind of sitting at L of 4, all the way down, though, to L of 1.5, right? You can see in the north, but focused anywhere between L of 4 and L of 2, okay? And then down in the south, right, these guys down here, right, between L and 2 and L of 4, okay? So rain current is down in this region, right? That's DST index. Aurora electrojet is in this region. It's L of 5, L of 4, and L of 5 and above. And so KP parked right in the middle, okay? So what does it get when we look further out, when we map that out into the magnetosphere? Well, it means you're getting a little bit of the field-aligned current system, right, which are on the front lines, right, because they're on the hairy edge. Some people have commented, I don't ever hear you use the word hairy. Yes, I do. I say hairy edge quite a lot. But here you're sitting on the outside, essentially on the very hairy edge of the Earth's magnetic system. These are the pawns in the chess game, right? They get sacrificed quite quickly to whatever the sun is shooting at us, right? And that sun may be just shooting a pawn at us, right? And a pawn fighting each other. So it could just be very little wiggles, and you're going to get a little bit of stuff with the AE index, but nothing else. But if what the sun is sending us is a queen ready to take that pawn, well, you're not just going to get the AE index to wiggle, you're going to get DST to wiggle down in here, right? You're going to get the lower, because it's going to peel all of that. It's going to take all your pawns and rip all that flux and fold it all back and expose the heart, the inner heart of the Earth's magnetic system, right? Because we peel that outer flux back, those high L shells, fold them back to the back part of and you just keep going in the sun, I mean, the Earth is trying to push more flux forward, but it really can't, because if it's peeled back fast enough, you're going to expose and you're going to crush and you're going to cause the L shells to be exposed and wiggle and have disturbances all the way down to the heart of the Earth's magnetic system, down in of L of 2, 3, 4, that type of thing. They're going to feel it. The flux may not be peeled back all that far, but it will be peeled back enough that these regions will sense it. They'll notice, because there's going to be a lot of disturbance in that, shuffling around in that region, okay? But remember how the flux gets peeled back, it's really happening more at the tail and coming forward. You're not getting a lot of stuff actually causing problems on the day side. You're just getting a lot of activity folding the flux back, and then and you get the slingshot that shoots all that stuff forward, and that comes from magnetic field lines that then follow into the poles, which is why you have aurora here. That's why you get it first at high latitudes. Okay, so the KP index kind of lights up when all of these regions are excited. or enhanced. Lots of KP stations, lots of them. Okay. What are there? 12. I think we have 12. There's here it's showing 21 results because some of these aren't they're not active. They've either been replaced or they're on hold, right? Because KP is one. That's the thing about these operational indices. You have to, especially with KP, it's such a critical index that it gets funding. And so you do have magnetometer stations that end up being replaced. You do have ones that are alternate. And as you can see, these stations in these latitudes are actually feeding a lot of different indices. Here's one, for example, that's feeding KP and ASY. ASY is very similar to DST. Okay. So you're getting a lot of these stations doing double duty from that perspective. And you can see some that say closed. There are some that are alternates. I think we have, is it 13? How many stations? No, 11. 11 northern and 2 southern. I'm getting bitten again. 11 northern and 2 southern stations. So here's our 2 southern stations, and then there's 11 that are active. And there are ones that are alternates, right, in case things go down. Okay. All right. So now we're going to, yep, there you are. Ooh, did I get him? No. That little mosquito, I'm telling you, I just can't believe he's still after me. Unreal. Didn't you get enough to drink? God. All right. So here's the interesting thing. Now, I have this one up because I always loved this aspect of KP. Believe it or not, the KP, we're going to actually start looking at the data itself, at the index itself and how it functions. And we're going to look at 2 different ways that it's been represented. And the first way we're going to look at it is actually the most insightful. It is not the one, it is still used, but it's I think, well, I shouldn't say that. It is still used, but it's not the modern way. I love the fact that the folks at GFC at Potsdam still create the old Bartels diagram, and I think they do it even more than for historical reasons. But I don't know too many people who use this particular version of the KP index anymore, but it really is one of the neatest ways of expressing the KP index in an almost artsy style. It looks very much like music notation, and as you can see behind me, this is the original way it was done. This is actually the scale, the key that is used, and you'll notice when we flip to a diagram why this is such a useful style of scale. It makes solar storm activity or storm activity at all really stand out very quickly. But if you ever want a really good description of the KP index, why it's here, when it was first created by Bartels, and really the methodology went through to create it, please visit this site. It's just an amazing site. I'll stand out of the way so you can see the link here. Now the scale, a lot of people know the scale goes from essentially 0 to 9. They may not know, however, that it's not just the integers. It's not just 0 to 9 through integers. You actually have 0 and a plus and a minus. So you can have a 0 plus, a 0 minus, and then a 1. Or you actually have a 0 plus and then a 1 minus, and then a 1 plus, and then a 2 minus and a 2 plus. So it's actually it's a way of kind of grading, making more divisions in the scaling. This is how you end up getting 28. I think there's 28 of these if you kind of look at this from that perspective. And I'm sorry, I'm very distracted again because this mosquito is just hovering all around me, all over again. My goodness, I thought I got through with this. He's back. He's back. He's back. Okay, so what I want to show you here in just a sec is if you look at, let's see, how do I want to do this? Yeah, I guess I'll put this in modern vernacular for now, but we'll talk about the color coding in a minute with what you see at the Space Weather Prediction Center and other places. We'll talk about that in just a minute, but I'll go over the numbers here. So in modern vernacular, anything from 0 up to just slightly under 4, so basically a 4 minus, maybe a 3 plus, would be what you would consider quiet to unsettled conditions. So when I talk about it in my forecast, for example, anything from 0 up to a 3 plus, I would say is quiet conditions. Okay. Anything from a 4 minus up to a 5 is active conditions. Anything from 5, 0, because you have a 5 minus, a 5 0, and then a 5 plus. Okay, if that makes any sense. All of these numbers, you have a minus, a 0, and a plus that you add to them that are these equal to gradations. So anything from 5 0 up to a 6 minus is what I call a minor storm. Anything from a 6 minus up to 9 is what I would call a major storm. Okay, and according to SWPC's old coloring, you would call everything from 0 up to 3 plus, that would be essentially green. The 4 minus up to about 5 is yellow, and then everything from 5, 0 up to 9 is colored red. Now they've changed their scales where they're now including shades of orange, and we can talk about that in more detail, but I think that's actually up on their website right now, where they're doing that, not in the old-fashioned KP diagrams, but in their real-time display of solar wind data. And so they're doing it to align, they're getting rid of their old stoplight red, yellow, green vernacular, and they're adopting a more shades of orange vernacular, which helps, but also, I don't know. I'm kind of ambivalent as to whether it's wonderful or not. So with that in mind, hopefully that helps get you kind of like oriented a little bit where the numbers are. But here's the whole thing with Bartels. Bartels doesn't use use colors. Bartels uses this very interesting scale. So as you can see in what you will see here very soon when I show you an actual Bartels diagram of KP, you will see these numbers, are these little lines, these vertical lines, okay, that indicate a measurement. And they will be all over the place. In this case, what you see is if it's 0, you're going to have a dot sitting on the origin, right at the baseline. As it grows up so you have a 0, you have a 0 plus, it'll be a little bit higher. So basically the 0, 0 is just below the origin. The 0 plus will be right on the origin. The 1 minus will be slightly higher, and you'll actually start seeing a vertical line drawing up to it. And as you continue to move up to the point where you get to 5, 0, you're going to have a vertical line that goes up to a high point. Okay, and you're going to see the horizontal bars are 1, 2, 3, 4, 5, right up to that point. Now, what do you do? Because that's as far as I want to go. They don't keep going up to 10. They decide that what they want to do is when you go to a 5 plus, now you will have it all the way up to 5. That's kind of maxed out. But now you'll have an additional dark line that kind of adds to the level where the plus is. Okay. And then if you go to a 6 minus, that you'll have your 5, 0, and you'll have that little black bar being a little bit thicker and a little bit higher. And again, you work up, so it becomes a second line that kind of chases the first until you get up to basically a 9 minus and a 9, 0, right? And you're basically, the 9, 0 is the highest. So what it tells you very, very rapidly, what it tells you is that starting around here at 5 plus, right, which is really into the first level of a minor storm. This would be solid red in stoplight chart. That's where you see that dark bar. So immediately your eyes will gravitate toward anything that has that heavy dark bar. You'll know that's a storm, that's storm level. Okay, and then the strength of that storm level is dictated by these secondary thicker lines. Whereas before, all of this is unsettled to active conditions. Get it? So it's kind of neat because Bartels instinctively knew to draw it like that so that your eyes would look at non-storming conditions and storming conditions in a slightly different way. Okay. So let's do one. Here's an old one. I may have another one. Do I have another one? Yeah, I did a 2020. So here's two different Bartels diagrams. And you can go to their website. And I didn't pull down one for today. I probably should have. But this is a Bartels diagram. This was done in 2018, October 31st. And what you're looking at in the Bartels diagrams is you're looking at 27 days. Anybody know why 27 days? Why not a month? If this were a Millersville class, I would actually wait for someone to respond to me. In this case, I'll just tell you. This is the length of a solar rotation. Okay, and sorry if you hear noise, that's a vacuum. It should be gone in just a minute. Today is distraction day. So what we're looking at is what we call a Carrington rotation. And so each one of these lines indicates a 27-day period. We are looking at 4 solar rotations from Earth's perspective. Well, 5 of them actually. 1, 2, 3, 4, 5. 5 solar rotations from Earth's perspective. The first one started June, right? You have the 19th all the way to July 15th. Then it goes from July 16th to August 11th, then September 8th, August 4th, and then October 5th to October 31st. So that's why this says until October 31st. Okay, so for 2018. Now, when I step out of the picture, outside of it looking absolutely devastatingly gorgeous and almost like you're supposed to play it as if it were musical staves, and this was a, Tchaikovsky's, Mach Schlav on piano or something. You can immediately see, or your eyes should immediately should gravitate toward 2 different intervals, right? Not the key. Ignore this. This is just the key. But there are 2 intervals that your eyes should almost immediately be gravitating toward. This one, right? Or this period in here, and this one. And rightly so, because those are the 2 big storms. Now, there are other intervals in there. Here's a little one. You can barely see, right? This one, barely see it. But for the most part, the 2 big storms stand out. Right? And that is one of the most amazing things about this particular way of looking at the KP index. If you want to really impress one of your friends and and say, and really show off, just throw one of these diagrams down and say, oh yeah, I can see. Oh my goodness, yeah, there was some strong storming in here and in here. Wow, yeah, look at that. And people will go, how do you make any sense of this? And you're like, oh no, it's easy. Just, it's magical. But you just don't tell them how. you just, show off a little, because it is really beautiful, isn't it? And it looks complicated. Man, this kind of thing looks complicated. But you can tell through all of this area that this kind of thing is not quite storm level, but close, right? And the big storms are here. But the other thing that you can start noticing is if you notice at the same time, or nearly the same time, in the Carrington diagrams, especially here and here, for example, you can start telling that these are actually storms that are likely from fast solar wind from a persistent coronal hole. Why? Because it's organized by Carrington rotation, by solar rotation. So every single time the sun rotates around the same part of that sun's face, the same features that were on the sun 27 days ago are there again, causing more havoc, right? This is a coronal hole. This is fast wind from a coronal hole. And sure enough, back in 2018, we were in the declining phase of the solar cycle, so that makes sense, because that's when coronal holes persist. And you can actually make a prediction with coronal holes that next month, at almost the same time, 27 days later, you're going to get another storm. And sure enough, you did. Right? Here's another example. This is in 2020. This is much closer to solar minimum. As you can see, not a lot of storming. No real big storms, right? Your eye immediately pegs this. The only one, I think, in this entire period. 2020 was a very quiet year for the sun. But again, see this? What do you think? same time in the coronal hole, you know, in the solar rotation, likely some fast solar wind from coronal holes. Okay. But neat, huh? Isn't this neat? I bet you never saw a KP diagram like this before, unless you're really familiar with it. I can't imagine anyone has seen it. But they do this every single day, and I think it's so fantastic. I hope they never stop. This is at Potsdam. Getting to a more common way of looking at it, this is what you find on the Space Weather Prediction Center site, right? This is KP in a stoplight chart. And once again, you're looking at anything that's green is basically 0 to 3, right? Now you've lost that plus minus stuff, right? It's just kind of segmented, right? Dink, 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 okay? But you get your color codes, right? So unsettled conditions, very, barely unsettled, almost quiet conditions. Active conditions, which is your yellow, which is a KP of 4. Storm levels, KP of 5, which is red. Storm levels, major storm, KP of 6, but still the same color, red. Even if it goes all the way and pegs up to 9, still storm levels. But notice, in the modern vernacular, you don't have the plus or minus. It's still there. As a matter of fact, in what SWPC is planning on doing now is that they are planning on showing decimal KP. So they're moving away from this vernacular where you've got your pluses, your 6 minus, 6 0, 6 plus kind of labeling, and you're just going into decimal. Okay. But you notice there's so much more detail in this than this. As a matter of fact, if we take a look directly, September 24th through September 29th of 2020. Let's go back here. September 24th through September 29th. It's basically this period in here. Okay. And you can see storm level, and you see 5. The 5 was right about storm, but you can see there was only one time where you actually had a real big storm, the KP of 6. This here is sudden storm commencement, which is right there. It's where you get a push, oftentimes a big burst of aurora right when the storms hits, and then it backs off. That's why a lot of times people get this false start. They see KP go up to 5, and they're like, "Oh, aurora," and then there's nothing. And they're like, "How could I have missed it? It obviously must not come from this far south." No, not true. Sudden storm commencement, meaning you get a big bang right up front. It's like when a bumper car hits you hard, right? That bumper, that may be all it is, just a bumper car because the field isn't configured correctly. But that initial hit of that solar storm hitting the front end of our magnetic shield can oftentimes cause a burst of aurora and cause a big magnetic field wiggle that will cause KP to jump up. And yet it doesn't really translate into aurora, which is one of the reasons why you look at other indices. You don't look at KP always for this. So believe it or not, though, what you just saw with Bartels and this, same index, just 2 totally different ways of representing it. Okay. And it's I guess it's worth to note, because what we're going to do now, I believe, is I'm going to start kind of comparing directly using the indices. I'm going to start comparing directly what AE looks like compared to what KP looks like compared to what DST looks like with some of these storms. Okay, so that you start getting a feel for really which index is the right one to use and why, right? When it works, when one index works and another one doesn't, and vice versa. Okay, so one of the first things I want you to see here, I love bumper cars, cute. One thing I want you to notice, and I wrote it down here, is that notice in this set of days, what is it, September 24th through the 29th, that really storm levels are very sporadic. Right? This is a reasonably weak either set of coronal holes. I don't remember exactly what ended up causing all of this, but probably a set of coronal holes, and maybe there might have been a coronal mass ejection thrown in there, because this is a reasonably long period of time to have storming on and off. But notice that you really only reach storm levels just very sporadically, which, if you're using the KP index, could be very, very frustrating if you're an aurora chaser. I bet a lot of aurora chasers got very frustrated if they were using KP, because by the time it went storm level, you're already out of it, right? So some of these are really either just quick sudden storm commencements that come on and leave faster than lightning, um, or they're really substorms that kind of pop up and get strong enough to sustain for a little while, but then come back down. We never got into like a really big storm period until about here. Okay, and then this is what I would call a geomagnetic storm. But this stuff, it's just really strong substorming. Now, some people might argue, some scientists might argue with me on that, but I would say that's, as we'll see in AE, the KP index, at least for this period here, was probably not a good, not the best index to use. Okay. And yes, the mosquito is after me again. My goodness, it's like a mosquito that wanted to learn space weather. So here's a couple examples of just KP, and we'll go, and we will be comparing some of these storms. Here is you can see a very short period, right, where you actually do have very quiet conditions, and then, man, you get hit hard, right? And it immediately jumps to KP of 6, even goes to a 7 before it drives down. But look how short, okay? This was for a storm back in May of 2017. Here is one of the classic Halloween storms, okay? Huge difference, right? This one reached KP of 9. Remember, 9 is as high as it goes. We'll talk about the limitations of that in just a moment. But know that this was likely off scale if the scales went any higher. But 9 is as high as the scale goes, okay? Look how many hours, days of over 5 kb. We'll talk about DST, okay? DST for this, not going to, probably going to be less than 100, maybe about 100. This, probably minus 350, 300, 350. I can't remember exactly. So we'll see so in this case, KP is showing you there's a storm, but the DST is not going to dive that deeply. This is going to light up DST like crazy. Okay. And the reason why I'm talking about this now is because I want you to start thinking about this, not just in terms of radio propagation or aurora chasing, but in terms of grid, okay? People always come to me and say, oh my goodness, there's a storm coming. Tamitha, is the power grid going to be okay? Power grids can handle this, no problem. Okay, as a matter of fact, even though it jumped up to KP of 7, okay, that's a G3 storm. Because G1 is 5, KP of 5, that's G1. G2 is KP of 6, G3 is KP of 7. Oh no, it's a G3 storm. For what, 3 hours? Really? Okay. They don't even put in mitigating procedures until a G2 level. And a G2 level at 1, 2, 3, 1, 2, 3, 4, 4 times 3, 12 hours, they can handle it, okay? Really, when it comes to power grids and geomagnetically induced currents, which we'll talk about a little bit, these types of things are only a real problem for power grids if they last a long time. If they're having to do this for 18 hours, 24 hours, 36 hours, 48 hours, yeah, grid's got problem, okay? Sustainability is a big problem when it comes to geomagnetic storming. Stuff like this, yeah, it reached G3, but is this a problem for the grids? Not really. Maybe in Sweden, but United States, the UK, not really. Canada even, not really. This, yeah. Okay, so keep this in mind. All of you who are preppers, are nervous, get scared when a solar storm comes. If you see a stoplight chart that looks like this, relax. If you see a stoplight chart that looks like this, now you can be worried. Okay, now you can say, okay, we might have issues. Is it catastrophic? No, this isn't, not by any stretch. We rode this okay. Were there damages? Yeah, this was a big storm. And the Halloween storms, you can look them up. There's all sorts of stuff being written on them. For that storm, this is now DST. Now we're talking ring current, okay? This was that storm. This is what it looked like. You get a bit of the sudden storm commencement. This is from part of the compression. It actually made the magnetic shield go higher, stronger, so the DST went up. And then the storm hit and it started causing the ring current to really increase. And so the depression of the field occurred. Okay. So oftentimes you will see that this was a fast storm. I mean, it hit Earth hard, but it wasn't super strong once we were actually in it. And it, a little bit over 100, or a little bit less rather than 100, maybe 125-ish, give or take an ish. So I said about 100. Yeah, okay. Not super impactful. This is the Halloween storm, one of multiple ones, right? This is a double dip, almost a triple dip. This right here is stronger. This tiny little dip is actually stronger than this whole storm. And look at it. It went off the charts. Why is it a double dip? Likely because in this case, we had northward turning, and then we got hit again by actually a second storm. And that really is reflected. Some people say, oh, well, DST and KP don't really reflect each other. Yes, they do. They do. There's the double dip. Okay. You got one storm here, got a little bit of a reprieve where things began to recover, and then you got hit by a second one. We had a really bad actor on the sun back then, and it just kept launching bad stuff at us over and over again. So here was the first dip. Here was the second dip. How bad were the dips? Oh, minus 400. Big storm, guys. Big storm. Okay. So when you get big storms, yes, you will see reaction from DST. Holding Merit, will you see reaction from DST? Okay. KP will respond quite dramatically. Okay. And I wonder if I have AE. So let's talk about AE, right? AE is the most sensitive of all the indices. So for the 2017 storm, here's 2 days, May 27th and the May 28th, right? That was the one where KP went up to 6 for a short bit, right? You had about 12 hours worth of storming, according to KP. DST went to maybe minus 125. Yeah, you know, you move the needle, but not super dramatically. What happened with AE index? Well, it started noticing stuff on the 27th. In fact, substorms became the norm, right? Anything over 500 for the AE, that's the top line, right? So you got some substorming here. And sure enough, all through the 28th, you're sitting at 1,000, 1,500. Here's where the storming really hit, because you're no longer seeing poof, poof, poof. You're no longer seeing brightenings, right? Like intensifications and then quieting, and then intensification and then quieted. You're just seeing pure brrr, right? Like machine gun. Well, that's when the geomagnetic storm hit. The substorms, people don't like me saying it this way, but it's almost easier to understand it this way. Substorms come so rapidly that they just kind of roll into one. Is that really the process? No, because substorms aren't always triggered by an outside thing. Substorms can be internal reconfigurations of the Earth's magnetic shield if it's unstable for whatever reason. Substorms aren't always a solar storm trigger, but you can say that as substorms become more and more rapidly triggered, eventually it just rolls into a big geomagnetic storm. It's like the substorms never turn off, and they just get bigger and bigger and bigger, and then it involves the entire system. The whole system goes up. And then, of course, as things calm down, you can actually see it in the AE index. You start seeing substorms return, right, where you get quieting and then substorm, and then quieting down, and then smaller substorm, and then quieting down. It finally turns off, right? Anybody who's an Aurora fan, this is where you see pulsating aurora. Anybody who's an Aurora fan, this is where you see Steve, right? Steve, or the subauroral arc, right, if you like to call it that. You also will see the subauroral arc, aka Steve, during this period. Oftentimes not pulsating aurora in the beginning of the storm, where it begins to like rise, right in here. You'll see the subauroral arc, but not necessarily pulsating aurora. Pulsating aurora much more often happens when you're in the decay phase. Okay. But do you see all that detail in the KP index? Not really. You get 12 hours of just storming, and then it's quiet again. Well, that's not really how it happened, right? So that's a minor storm, but it lets you see, even with a G2 level storm, even it pops up to G3 level for a short while, AE can handle it, right? It does okay. right? You don't get a lot of detail because it begins to get smeared out during, you just know that there's a lot of auroral activity, but you don't really kind of know how far down it gets. How far will aurora go in terms of going, toward the equator? Well, that's more of a KP thing, right? You start knowing that it's going to be in real mid latitudes, not by AE so much. You just know here aurora is lighting up at high latitudes. But if KP starts lighting up, then aurora really is beginning to dip down to mid latitudes, right? If you see it in DST, well, but it has to be pretty strong. Minus 100 is not really super strong. You're going to see it at mid latitudes, but probably not really much lower than that. How about for the 2003 Halloween storms? Remember, AE index is the most sensitive index we have. Do you find this readable? Now, for those who love AE, don't worry, I will give you the caveat that this is just an error of the plot. It's not that AE can't measure, but if you're going to look for real-time AE data, the AE index data, you're likely going to be disappointed if you think that during a KP9 storm, where it's lasting for 48 hours, 72 hours, right, of pure storming, that the real-time AE index data is going to be useful. You got something coming, It's not. It's a joke. AE is off the charts, right, in these automated scalings. In fact, it's so off the charts. In some plots, you actually see AE, in some of the plots that I've seen, AE will actually wrap around and you'll see it at the bottom of the chart poking out from the top plot because some of the plotters just kind of wrap the vertical axes around. It's pretty funny. I might even have a plot like that shows you that. But as you can see, it slammed super hard, right? And you can see it was just completely off the charts. Remember, all you need is AE to be about 500 to get substorms. When has this ever calmed down from 500? It doesn't. I mean, not until finally here, right? Not until finally the next day. And then it quiets down and then the second storm hits. So can you tell that, there's a double dip? Sure. Here's one, right? Here's the quiet in between. Here's two. Easy to read? Not really. AE gets saturated. Okay, at least the real-time data does. Let's put them all together. So for minor storms, even up to a G2 or G3 level, but mainly a G2, essentially, it's KP6. AE does really well. AE is the real-time AE data is really, really great, right? Because it can show you when substorms are. So if you're at high latitudes, it can show you when to check for aurora. And I mean, it's really spot on. I've had aurora photographers, literally, I'll say, okay, in 5 minutes or in 10 minutes, you should see an intensification. And they do. I mean, it's just, AE, it follows very, very well. And then you can tell where the really heavy storming is occurring. And then you can see when things are calming down. So you can actually catch features of the aurora when you follow AE. High cadence, high sensitivity, really good index for that, for minor storms. DST, worthless. Right? You can chase aurora, you're going to look at propagation based on this? Probably not. Right? KP? Okay, maybe, sort of, kind of. Remember, this is 3-hour delay. So while this is coming out in real time, you have to wait 3 hours for each one of these blocks to come out. But does it let you know that the aurora is reaching mid-latitudes? Sure does. Does this really let you know that? Yeah, not really. It just lets you know that a storm is happening and it's pretty strong. Okay. How about for a big storm, KP9? AE? Maybe a little bit over here before it ramps up, the second time. First time, not a chance. Look at it. It's just nothing. It's like a light switch. Just slam. It's just on, right? Remember, 500 is here, guys. So could you tell the difference between brightenings and non-brightenings? No. With the storm? No. As a matter of fact, if you're anywhere where the KP index is, if you're in the northern hemisphere, you're no longer looking north. It's guaranteed that aurora went right over your head, and now you're looking south at the aurora, if you can see it at all. In many of these areas where you would normally use the KP index, if you're at those high latitudes, aurora is not even on your southern horizon. It's dropped so far down to mid-latitudes, it's over. KP index, is it useful? Yeah, to say, oh my God, this is huge, right? It's being saturated. because it's being off scale. You see a little bit of, you can tell it's a double dip kind of thing, but it only just tells you, oh my gosh, this is a massive storm. Where's the detail? Ring current, right? Ring current. But obviously, if you're in a storm like this, you could be pretty much anywhere on the globe and know something's wrong. Why isn't my GPS working? Right? Yeah. Oh, why is the sky lit up? I'm in South Texas. What's going on here? So yeah, hopefully this gives you a decent look at the indices to kind of give you an idea of when AE is useful compared to these others, and when DST is useful compared to these others. Okay. Here's the SIM index. As a matter of fact, I think I might even have AE on this. No, I don't. This was for October. This is for the Halloween storm. So you see, here's AU and AL, not in real time, obviously, historical data. You can put these on a map where you can actually get useful information. It doesn't have to be completely smeared out, but this was plotted afterwards. Okay. In real time, you're not getting the data very well. Look at this. I mean, look at these peaks. These peaks are about minus 4,000 in the lower. Okay, so these are pretty intense. The electrojets, both the east and the west, are lit up. And I forget if the lower electrojet, the west one, I forget. I think it is. I've forgotten at the moment. And then you look at SIM-H, right? Look at this, minus 500. Okay. You're getting detail. Remember, the SIM-H index is showing you higher resolution data than KP. Than DST. DST is an hour index. SIM-H is minutes. Okay. So you get a little bit more detail. But if you're hitting a storm that is so intense, you're really what you're talking about is stretching out time so that your recovery is no longer recovery on the time scale of the AE index. It's recovery over the time scale of days. So Aurora actually took a while. I guarantee you this storm was likely over. The field could have easily flipped northward at this point in time, but it literally took hours and hours and hours and hours for the aurora to finally die down, because everything was so spun up. The convection patterns and everything was just so crazy that even halting it is like that flywheel where you have to kind of and spin it down and get rid of all that excess energy in the system. And that's what the recovery phase is for. But it literally takes days. Not to mention that the sun was probably still throwing stuff to slow the recovery down. Okay, any questions on that? I'll get to the local K in a second. Any questions, guys? Does this make sense? Did this help? Hopefully, kind of get you calibrated as to where, which index to use and why, and what they're good for and what they're not good for. South Texas, it's where you are. That's right. Yeah, pretty hot there. Pretty humid in many places in South Texas. Not East Texas, or not West Texas, but East Texas. Yeah, it helped a lot. Oh, good, Julian. I'm so glad. Okay. Yeah, your mom claimed it was seen in Texas. Yes, absolutely. Mike Richardson knows. If Mike is still with us, Mike Richardson knows that, what was it? It was the 1989 storm. So find out if that was a 1989 storm. That was March of 1989. Lots of people in Texas saw it. They actually thought it was fire. There were paramedics and firemen and police being dispatched to many different places in the southern region. People saw it in Louisiana. They saw it in lots of places. March 1989. Yeah, Mike, where were you? Ask Mike about it. Sorry, Mike, if I'm inundating you with questions, but Mike has some amazing photographs that he took. He actually had to educate the police, I think, on it. Yeah, so ask him about it. He knows lots of stuff regarding that storm because he personally experienced it. I'm hoping that we're going to get a lot more of that. Not so much that we want big storms, but rather we're going to, in this solar cycle, because the space weather community is so much more savvy now, And we have a lot more scientists in the loop that are, explaining things and giving nowcasts that are much more reliable than, trying to tackle these indices on your own. That we're going to have a lot more people out with cameras and out with cell phones. Our cell phones have gotten so amazingly good. The cameras in these phones, they've gotten so incredibly sensitive that they can spot auroras so quickly. And so I can't wait till we get, a decently sustained, let's say G2, G3, maybe even a G4 level storm, that isn't happening at 2 in the morning. That's hitting hard, like at 9 o'clock at night, in the Western hemisphere. And, or even in the UK, and then in Europe, and then it travels across the pond to the United States. So both hemispheres get a really good shot, and then it continues on so that New Zealand, Tasmania, and Australia get a good shot. Something like that, where it's a sustained thing over a long period of time, would be so wonderful, because everybody's going to know about it, and they're going to be out with their cameras, and we're going to realize that even with a G2 or G3, G4 level storm that's sustained, that we're getting aurora in places that we never thought the aurora would come so far down to. And we're going to see that aurora is not nearly the elusive phenomena that we've been trained to believe it is. Aurora really is for everyone. And as we get closer to solar maximum, I'm sure hoping the sun's going to send us more frequent storms that are at that level. I'm sure the power grids aren't going to like me for saying that, but they can handle a G2, they can handle a G3, for especially if they get breaks. And I think it's going to really up our ionospheric science and our aurora, our magnetospheric science, and these nowcasting and these operational disciplines that are just in their infancy, because it's so important, especially now with everybody, with us becoming spacefaring and having these Leo constellations in the sky. We need to be so much more savvy. And aurora tourists, we're space tourists. We need to be so much more savvy about how impactful these phenomena are. And I think we've only scratched the surface of our true understanding. So anyway, hopefully that helps everybody understand this. Let's see. Thank you, Tamitha. Very clear and concise. I've been a bit unsure of how to use the data sets thus far, and I'm still new to the index side of things. Yeah, despite being a lifetime sun watcher. Well, that's just it. I want to be able to help bring these indices to you. You guys have come to the indices for so long with very little help in terms of getting the definitions. Partly because the indices were never meant for the public to be used in without a scientist in the loop, and partly because some of these indices, they just were never designed with this in mind. Our field, at least the operational side of space weather, really has a big paradigm shift to go through, and I think we're beginning to undergo it now, where we are going to become more and more like terrestrial weather, in the sense that forecasting is going to become more important, and creating data products that are understandable to the non-expert are going to become more important. That's why I work so closely. I try to work so closely with terrestrial meteorologists, because that really is where the precedents are set for space weather. Terrestrial meteorologists are really savvy. They've already gone through these growing pains, and they can help our field immensely, where the academic side of space weather doesn't really understand it, because it's just not something they look at. They look at societal impacts, but they don't look at it as weather. They look at it as astronomy, and it's really the operational side of space weather is far more like terrestrial weather. So it's that bridge has just yet to be closed, but or made rather, and it will happen. But I think terrestrial meteorologists and storm chasers in the terrestrial sense are going to help us a lot in that to get through this kind of really bizarre period we're in right now. Okay, so one more thing I wanted to show you, and I may have to close it up after this because we've been on for quite some time now, I think. But one more thing I wanted to show you was the the usefulness of local K stations. And I wish more, and believe it or not, the USGS used to put out a local contour, a local K map, where you actually could have a map of, in this case, it was only the United States because it was only USGS controlled stations. But they would take all the magnetometer data and turn them into K indices. And then they'd make a contour map where you could see where locally the K was, its storm level compared to where the K was sitting at unsettled. And you could start really seeing how those maps indicated where the I don't want to say the trouble zones were, but where the wiggles, the magnetic field wiggles, were really out of control at that time. And I was noticing early on when they were doing this that a lot of the amateur radio operators were telling me that from their anecdotal reports that these K maps, when I would give them reports about their local K index, it really would coincide with disruptions in their propagation, especially on the night side. It was very interesting. But sadly, that the USGS stopped doing their maps. What they do now is, yes, I am chasing that dang mosquito again. What we have now, though, are, at least for SWPC, the Space Weather Prediction Center, they do have K maps, or K indices rather, for different magnetometer stations. Boulder, Fredericksburg. There's the planetary KP. So this is KP, right? These others are just K, and then here's College. So you've got, these are different latitudes, and so you can imagine in that in that area, in that regime, where you have all these stations. Let me go back to it, right, for just a sec. So in this regime where you have a lot of these K stations anyway, and I wish I'd see more of them for this. I see magnetometer stations and magnetometer data for Europe, but I don't see a lot of K, local K indexes created. And maybe I'm just not looking in the right place, but it'd be nice if I saw more of those. But you could conceivably take a single station and take that magnetometer data and turn it into a K index, right? But it would just be local, and that's what you see here. So there we go. So as you can see with the planetary index right here, and I believe I have, is this May 26th? Okay, so I have this highlighted here as being akin to this. Okay, this is the planetary for those 3 days, 26th through the 29th. In the plot I'm covering, you'll see that this one bar where we got to a KP of 7, which is a G3 level storm, in this plot behind me, it's labeled purple. It's no longer just red. So that's what you're seeing here. Okay, but notice that depending upon the latitude of the station, whether you're at Boulder, Fredericksburg, or College is a bit sensitive. You do see slightly different K values. So both at Boulder, you actually got an impact earlier and it jumped up to active conditions, and then back down to unsettled, and then it jumped up to a KP of 6, or I mean a K of 6, sorry, locally, right? So a slightly different activity level. Whereas at Fredericksburg, slightly different latitude, stayed at unsettled, but jumped up a little bit more intensely. You got to a KP or a K of 6, and then stayed at a K of 5. Okay, so less intense than College, and much less, less intense than Boulder, and much less intense than the College station. The College station, because of its latitude, ramped up just almost slowly, but completely, until it got to, my goodness, it went off scale, KP of 9. And then it jumped back down to 6. Is that the sensitivity of the station? I don't know this, but College is always has been a very sensitive station. And there are local anomalies in Earth's magnetic field. And remember, the Earth's magnetic field isn't a perfect dipole. Oh, this bug. The Earth's magnetic field is not a perfect dipole. It has the dipole field, but it also has the the quadrupole field, the octopole field. It has those multipolar field components underneath, and those cause anomalies I want to say I shouldn't say anomalies. They cause variations in our magnetic field signature, in our magnetic field strength. And then you also have all of the geological formations that cause discrepancies and anomalies and variations in our overall magnetic field signature. And a lot of that stuff has to do with the bedrock, right? It has to do with the conductivity of the ground, the kind of bedrock it is, whether it's mountainous or it's flat, whether there's water underground. There's all sorts of things that cause that. This bug. I'm itchy. So not every locality is going to respond magnetically the same way, right? And that's why local K indices can be extremely useful. Granted, they're still 3-hour cadence, but they're still more useful. Okay, so if you have a chance to find a local K index, you interpret it the same way you'd interpret the KP, but you can interpret it locally. Right, yeah, now I'm going to do one more thing, and then I will call it, because I'll have a really good place to stop. So this one more thing I want to talk about is really you remember how we talked about SIM-H being the high cadence version of DST, right? The DST historically it's a 1-hour index, and that's great, but as time goes on, we're finding it's not so great to be able to study. There's these other high speed, high cadence processes that we want to study, and yet we can't really change DST because then it makes it invalid for comparing to historical events. So we have to come up with new indices that are higher cadence, higher data rate, that type of thing. And so SIM-H was made. Well, believe it or not, KP has the same problem, right? It's a 3-hour index. We know that's not good. And so recently, we've created our field has created, scientists in our field have created the HPO indices, okay? The H means hourly or half an hourly. P means planetary, just like in K, right? KP. So it's still a planetary index. But O is now open. And what that means, open-ended, is that remember how we saw this? Let me go to, remember one of the biggest problems? I mean, not only do we have the problem of 3-hour bars, right? 3-hour bins averages over time, and that's a bad thing. But remember how we talked about KP just going to 9 and stopping? So anything off the charts is kind of lost, right? It's a close-ended system. Well, the HP system, the HPO system rather, wants to ameliorate that. They want to get rid of that. They want to have a higher cadence, so it gets rid of the 3-hour limitations and smearing out, but also get rid of the open. I have no idea. Yes? Hi. What do you? Hi. Finish?
Yes.
Please talk to my husband. Kent?
Your husband?
Yeah.
Nicole?
Is he not here?
I don't know.
Oh my goodness. Hold on one second.
I'm sorry. No.
Are you guys, is anybody else recognizing that this is like the distraction central today? Oh my Lord. Okay. Oh my Lord. Oh, this is nuts. Today is just, this is one for the record books, definitely. Okay. Where was I? Okay, so HPO. Did I ever tell you these courses are informal? Let me reiterate, these courses are informal. And that was about as informal as it gets. Okay. So, so we have an a closed-ended system with KP, right? It only goes to 9, right? And we want it to be able to extend beyond that because there are obviously storms that are stronger. And I could show you a couple there. I'd have to grab a couple where you see it pegged at 9 and it just stays at 9. Like for instance, in here, right? We know that this was off scale. So the HPO system is designed to, in a sense, set a new standard. Okay, and they're reasonably new. And Jürgen is if you go to the Potsdam site, Jürgen is the one who takes care of this, and I blacked out his phone number. Yes, you can find it right there on the website. Please don't call him and harass him, just if you have major questions or issues with getting access to it. But all of the data, again, this is a wonderful website, and these guys are very, the whole team in this center are extremely detail oriented, and they have outlined, they've taken an immense amount of time with their website to give just a ton of information about their data sets. And so you can access this stuff very freely, both the data set itself and images. I think, where are the images? Shoot, maybe I don't have it on this. All right, if you scroll down, I think if you scroll down, you can see the images. But there are graphs as well as data sets, so you can plot it yourself or just use their setup images. And I'll show you some of their images in a second. You have both the HP30 and HP60 data sets. HP30 is every 30 minutes. HP60 is every 60 minutes. So you basically have half hour and hourly indices, which is why H works for either. Okay. And open-ended means they don't cap it at 9. Right? It goes higher than that. So if you want to know more about it, there's an open paper, a GRL paper that came out just recently, as a matter of fact, back in May of this year, by Yamazaki, I believe. Yeah, Yamazaki et al. And what's nice, again, they've labeled where you can get the data. And the nice thing is that they actually describe, even in their oops, let me get on this side, even in their introduction, a bit about what HP is and what it stands for. And they do a really nice review of what KP is and why HPO was created and how it's different and how it's the same. They do use exactly the same observatories, okay, as KP data is used. And yet, because it can't go back to 1932, which I believe is when KP was started, it only has from 1995. Okay, because we just didn't have the data processing at that time, or the data, I don't think we have the data archive that is at high cadence prior to that. Okay. But here's what the data looks like. Okay, and I didn't go and grab big storms. I didn't have time to go back into the data and grab big storms, but what I wanted to show you were two examples of, and I'll probably stand out of the frame here in a second, two examples of what their nowcasting data looks like. If you were to go to their graphs and just wanted to look at something, not take time to plot it because you're busy, you're on the road trying to get to your Aurora destination or whatever it is, you just want to get something quick and dirty. This is what their plots look like, both for the HP60 index, as you see here, right? This is the hourly index, and then the HP30 index, which is their half an hour index. Okay, so the top plot will show you one full day, and they'll populate it as the time goes on. So I grabbed this, I think, early this morning or late last night, my time, which is not UT. Obviously, this is in UT. And you can see, right, the half an hour index will have twice as many bars as the hourly index. But what's nice is that it's done in exactly the same fashion as KP. So you don't have to learn anything new in terms of interpretation, right? It's just a higher cadence index. And it'll go higher than 9. Right? They just have 9 here at the moment. But if it needed to go higher than 9, it will. Okay. The bottom plots are showing what it's been the past day, past week, essentially, the past 5 or 6 days prior. So the whole thing together shows an entire week, entire 7 days, for both the hourly index and the half an hour index. And don't worry, I'm going to zoom these in just a second so you can see the difference. Now, by contrast, here is the SWPC KP index, okay, for essentially the same time period. Actually, wait, no, sorry, my fault, not the same time period. This is 3 days, okay? And so if you want to compare directly with this plot and this plot, you're looking at just this tiny little bit. See the difference already? In SWPC, in the KP index, the standard KP index, we have essentially 2 bars. In the half an hour index, we've got a lot more detail. And even in the hourly index, we have more detail. Okay. So suddenly KP becomes, using the HPO indices, even using the hourly HPO index, suddenly we get a little bit more insight into what's going on, and potentially this becomes an index that might be useful to aurora photographers. Okay. Especially aurora photographers at mid latitudes. Did you guys hear that? At mid latitudes. Okay. So while the AE index is great for people at higher latitudes and even in the top tier, I mean, the highest portion of mid latitudes. So like the American Canadian border, for example, right? Or, anywhere in southern, I'd say southern Tasmania, southern New Zealand, right? AE index is great. But what if you're Iowa? What if you're South Dakota, right? What if you're, Auckland, New Zealand, right? You're up at the higher levels. Or even Victoria, Australia. Well, maybe the AE index isn't so great because it can get overwhelmed and you're still not sure if the auroral oval is going to come down. But this HP 30, HPO 30, maybe so, right? So let me blow up and show you the detail. So this is what I've done here, and I'll stand kind of out of the plot. And I should have labeled this, and I apologize, I didn't take time to do that. But you can imagine the lower resolution stuff is, you just see this disembodied arm here. Hello, hello. There's just, you can tell that this lower resolution stuff is the hourly, the HP 60, and the higher resolution with a lot more bars is the HP 30, okay? So what I'm gonna do, actually, I'll just stand on this side, and we'll do this one at a time. This is the 31st of July. So this is just recent data, right? Which has been, for the most part, quiet, right? If we go back to the AE index, the KP index, it's all been unsettled, right? According to KP, unsettled to quiet. Well, not according to the HP index, okay? According to the HP index, look at this, back on the 31st, the hourly index shows, this is, I believe, a K index of 4 and a 4.5, okay? And you can see there's two of them that are yellow. And then it went quiet, and then it got another yellow bar. Okay. Here, there's even more of them. Right? You can see a bit more detail. And then again, August 1st, you also got a little bit of active active condition, planetary. It just didn't last long enough for it to register in the classic KP index. Right? And again, unsettled here. Look, but there's in the hourly index, it's all unsettled. But look at here. Higher resolution, for a short while, there was a little bit of activity. See the yellow? And again, on the 3rd, again, a short while, there was a little bit of activity. Okay? So you begin to see that you can get detail in the HP indices that you don't get, that gets smeared out in KP. Here, by contrast, is the KP index for this entire period. Okay? Everything that's highlighted in yellow. All you see is unsettled to quiet conditions, completely, without a doubt. Yet, higher cadence reveals detail. That there was a little bit of active conditions. And granted, this was from that solar storm that we had recently, the fast solar wind that had the coronal hole with the wrong polarity, wrong magnetic polarity. It's a Russell-McFerrin effect for anybody who's wondering why I talk about magnetic polarity when it comes to coronal holes, and how I knew that even though we got some decent fast solar wind, it wasn't going to give us much. It has everything to do with the fact that we're moving away from the solstice on our way to the equinox, and we're in the fall, and therefore a certain polarity of coronal hole will give us the right magnetic configuration to couple better into the solar wind. And this particular coronal hole really didn't do it. That is a different topic. I don't know if I went into the Russell-McFerrin effect when I was talking about the solar wind in one of my mini courses. Did I ever go over that with you all? I forget. Somebody remembers that, they can let me know. If not, I might do a specialty course on that at some point. And then, oh, my fault. I'm sorry. Hold on. Let me go back. This, I did it twice. This is August 4th, 5th, and 6th. So my apologies. August 4th, 5th, and then, yeah, oh, sorry, just 4th and 5th, sorry, 4th and 5th. So it's just these 2 days. So here in the KP index, you see nothing that even comes close to active conditions, maybe just kind of an unsettled right here. But if you actually go to the HP indices, you do see this being active for some time, and even here you see it active twice in this higher resolution in the 30-minute index. So you did reach active conditions. It just didn't last long enough for a 3-hour average to show you that. Okay. So when people say, my goodness, I can see aurora when KP is 2. Well, yeah, because it's smeared out. But look at your higher resolution K indices, and you'll find that likely something popped a bit higher. It just didn't last that long. And you just happened to be in the right place at the right time. Well, these indices allow you the chance, a better chance of being at the right place at the right time, because you'll see it, right? And it'll also be updated faster. Now, this part here is for the whole week. So now I've highlighted July 31st through August 5th. And again, there's one period on July 31st where KP actually showed that there was active conditions, and that was here for 1 3-hour period. But in actuality, it really was only 2 of the 3 hours. See that? So here's an example of where a KP60 is showing 2 hours of activity, and yet this is showing 3 hours of activity. So here's where KP actually overshoots. In many areas and many times it undershoots, but in this one it overshoots. So KP can err on both sides. KP can give you a rating that makes you think aurora exists where it doesn't, and KP can fool you into thinking aurora is not, there's no chance for aurora, when actually it's right nearby. Okay, that's the problem. That's both the pluses and the minuses of KP. Okay, but HP might really be a very good index for those of us at mid latitudes, especially when you start talking about HP 30. Okay. Sadly, we don't have HP 30, I believe. Well, it's using the same stations as, I shouldn't say sadly then, it's using the same stations as KP. So the nice thing is that it's still relevant. You know, even though this data is being processed in Potsdam, it's not just a European thing. It's still a planetary measure, but it is giving us a little bit of insight, a little bit more insight than what we would have had in prior to. And it's probably the best for mid-latitudes. It probably still is the best mid-latitude indicator, at least the high-resolution stuff is, for both propagation and aurora. It's just the best we've got. Maybe not so useful for power grids unless they're really advanced and they want to know whether or not they're going to get kind of a reprieve. Because when you have solar storming, you get these geomagnetically induced currents in the ground, and you want that to back off for a little while because transformers heat up, and especially old transformers are extremely susceptible. And we'll get into that next time. I'm not going to go into the GICs this time. I thought I was going to get there, but we didn't make it. So that'll be one more course we'll do probably. Then that will probably be the end of the ground level stuff. But if you're an advanced GIC studier, then I could see HP being useful to you. But KP is also extremely useful because transformers and power grids, they're slow to ramp up and slow to ramp down when it comes to at least slow overloads. Now, we're not talking about EMPs. We're not talking about the sudden storm commencements where, some of the biggest storms on record, power grid shut down in less than, minutes and seconds in some cases. We're not talking about those intense storms. We're talking about storms that put a load on the grid for an extended period of time, where you actually they have a chance to actually mitigate things. That's where indices like this could be useful to let them know when the loads are going to relax a little bit compared to when they're ramping up. You could actually see the ramping up and ramping down of these loads. And that might be useful to grid operators who are advanced in this. Otherwise, KP really is still the better indicator for them because it's kind of like, it's a stoplight, right? It gives them, it's crude enough to not overwhelm them with information and confuse them, but it's and it's simple enough to not make them overthink it, but it's also it's got enough information and enough enough understanding of enough capturing of the planetary scale of things to let them know when problems arise, right? When something is going to continue to be a problem. So, power grids, it's a little bit of a touchy thing, but really what we've been talking about and focusing on today is more about people who are, GPS users, for example, and you don't want to fly under Aurora. So you need to kind of know where these indices are and what they're doing, because you need to know where Aurora is, right? Obviously Aurora chasers, right? Super important for you. Any type of storm chaser, whether you're a terrestrial storm chaser and a hopeful solar storm chaser, or you're trying to capture that, the coup de grace, which is having a big thunderstorm along with Aurora, that kind of thing. Or you're an amateur radio operator, and you worry about propagation. These types of indices are extremely useful. But AE for high latitudes, KP or HP really for mid latitudes, and then if you want to know really, really big stuff, then we start going into DST. But if you ever wonder why a lot of us scientists don't use DST when we're talking to you about aurora or propagation, now you kind of understand why. It's much more useful on a larger scale when these storms are really, really big. It's by that time the Earth is so engulfed in aurora, just look up. If you're getting aurora down in South Texas, you don't need to worry about DST. DST is kind of, everything's going to be lit up like a Christmas tree. So by that time, DST is, it's more from an academic and a scientific perspective, letting us know what's going on, rather than something that you guys would use. So with that, I think I've come to where a good stopping place for us. Yeah, because the very next one I'm going to start talking about the grid. So I will go into this next time. One thing I do want to do before I completely let go is that I had and start answering questions, is I did have someone, I forget, was it Julian? I forget if it was Julian, if it were you. You had asked me specifically, or someone had asked me from Patreon specifically about animals that sense geomagnetic changes, right? And sense these storms, and how do they affect them? And we've been learning a lot more about that. I mean, some of these articles have been, and these things have been known for a long time. But some of the things that I find most interesting are some of the mistakes we've made as scientists. We used to always think that there is an internal magnetic compass inside animals, that when we have big geomagnetic storms, like big beach, whales would beach themselves and things like that. And it's not always geomagnetic storms, believe it or not. A lot of times it is with certain animals, but not always the ones that you think. For example, birds do recognize Earth magnetic fields, but not necessarily through some internal compass in their head, but rather through their eyes. They actually see it. And you can find this everywhere. If you just Google, there's a lot of studies that have been done now. And apparently they actually can sense where the magnetic field gets stronger and where it gets weaker. And it's relative to some sensors, some specific receptors they have in their eyes. And so things get brighter when they fly in a certain direction that's aligned along Earth's magnetic field. And we're thinking that this is the reason why homing pigeons have so much trouble. And yes, racing pigeons do get lost during geomagnetic storms because of this local field is wiggling, right? The K-index is all over the place, and they happen to fly through an area that's like that, or in an area where that's happening. They're going to get confused, and they're going to think that they're flying a certain direction when they're not. And so they get lost. And this is finally, we're finally beginning to realize it. It's due to, so I'm reading it right here. It's due to a particular kind of protein that is in their receptors. And like I said, there's a scientific paper on this that's done in medicine. I forget, I didn't have time to pull it up. I just did a Google search because I knew what to search for. But there's a lot of, I mean, this has incited a lot of interesting research, and it's caused some people to wonder, if birds have it, do humans have it? Do some humans maybe have something like this? Is there a potential vestigial thing? Could we have actually been susceptible? And that's why some people get headaches, and that's why some people get migraines, because there's something subtle, but you know, um, and visibly indetectable, imperceptible, but still there, nevertheless. So it's beginning to prompt a lot of interesting research in humans as well, because there is undeniably a class of human beings that are susceptible to geomagnetic storming and other things. Another big one that was interesting, and this one actually surprised me. And again, I just pulled it up on Google because I knew it to search. But beached whales, and I'm sorry, that's a really horrible picture. Gosh, I shouldn't have shown that. Ugh. I'll stand in front of it. But I was trying to show the title, the surprising link between solar flares and beached whales. We have thought for so long that when we see these beachings and we see these stranded whales that people are pouring water on and they're trying to shove them back, and then they just keep coming back to the land. We thought for so long that they were during geomagnetic storms, and there was a lot of support for that, but it was always a little bit fuzzy. We'd have studies that say, yeah, there's a trend, there seems to be a positive correlation, but it's not as clear as we'd like it to be. Well, believe it or not, about a year or two ago, I remember reading a paper on this, and what they found was that they were conflating space weather phenomena. So that it turns out that, yes, it was space weather that was beaching the whales, but it wasn't a geomagnetic storm. It wasn't because of the Earth's magnetic field. It was actually due to the solar radio bursts that occur during solar flares. And if the solar radio burst was in the right frequency range, it actually would mess, if the whale was on the day side of Earth, obviously, it would actually mess with some of the chemical some of the chemical processes that were going on in the brain of the whale, because these whales have, they have all sorts of different types of communication techniques and things, and so their brains are wired differently. And I don't think we completely understand it. At least we didn't as of a couple of years ago. But because solar flares, right, and coronal mass ejections oftentimes happen together. Well, a coronal mass ejection, right, launches during, you can have a solar flare with a big radio burst, right? And this is, if you're not familiar with this, go back to my mini courses on coronal mass ejections and solar flares, and you'll recall the details, which is that solar flares and coronal mass ejections often happen together. And if you get a solar radio burst during a solar flare and a coronal mass ejection is launched at the same time, and the radio burst that occurs is occurring, in the right frequency range, is a high enough energy and high enough frequencies that are being let out. Check. Okay. Sorry, just heard something on my phone. That those radio bursts that are reaching Earth right away within 8 minutes of that solar flare, they're affecting the whale at that time. Meanwhile, that coronal mass ejection, which is the slow mover of the group, it's really slow. It's moving about, 800 kilometers a second. Yeah, real slow, but relative to the speed of light, pretty slow. So it reaches Earth in a couple days on average, maybe a little bit less if it's super big. And so it causes a geomagnetic storm, and the whale beaches itself. Well, what we didn't realize is that the whale was already getting messed up from the radio burst that happened a day prior or 2 days prior. But it still was correlated with that geomagnetic storm that occurred at Earth because the coronal mass ejection came as well. So they were conflating the two. And it took a bunch of savvy scientists, and I'm sorry, again, I didn't pull up the original study. I believe I did this in another mini course, and if we talk about maybe the medical database that we're putting together, and if I ever do a mini course on that, we'll talk more about that. And I'll be sure to credit the proper scientists that did it, but I'm sure it's in any of these articles here. But what they realized is that the correlation, when they excluded geomagnetic storms and just did radio bursts, the correlation went off the charts. I mean, it was an insane correlation. And then when they added back in the geomagnetic storms, the correlation went down, and it went back to what we had seen it was commensurate with what other articles had already been previously written trying to correlate these geomagnetic storms with beached marine animals. So it was very, very interesting in that, you know, as implausible as it might seem, the data doesn't lie. And so the scientists were left to say, well, you know, it's got to be these radio bursts because that's what the data is telling us. And so they did more digging and they realized that, yeah, we think that we see some mechanism by which it's happening. We're just not we're just not totally sure how that mechanism is, you know, exactly how the mechanism is working. But we do see a connection and that there is something plausible. So there are two examples, right, of you know, animals, birds, and in this case, marine mammals that are, you know, that are affected by space weather explicitly. And so, you know, a lot of this, I'm not saying that all this has sparked interest in humans, you know, work on humans, but I think it's getting a more of a foothold as we begin to realize that, you know, mammals are affected, and there are plausible mechanisms for this, and as we begin to start peeling back the separate phenomena that are space weather, instead of lumping them all together as one big thing, we'll start pulling out more correlations, and we'll make more sense of it. But we're still in the beginnings of this kind of research, and yeah, it's very fascinating, very fascinating. So those of you who are affected, you know, for all sorts of different reasons, and I've talked about a lot of the different reasons, you know, especially if you've had medical devices implanted in you, or, you know, plates and screws, or you have heavy metal poisoning. I've talked about a lot of this stuff. You could very well be in a sensitive category just by the augmentation that modern medicine has done to you. So, you know, take heart, because answers are coming. Answers are coming. So hopefully that was enough of a little answer to your question. I think, Julian, I believe you were the one who, here, let me get off of this really awful picture so nobody has to look at that awful thing. I don't want anyone to feel badly about the whales. Sorry, I just grabbed something right off of Google. I didn't I didn't check to make sure that the picture itself was a good one. But let me see. Was it Julian? Was it you? Yes. What knowledge do we have on animals' orientation based on magnetic currents during major space weather events? Yeah. So hopefully that helps start that dialogue. If you want to have more dialogue with me on Patreon regarding that, we can. I didn't get to the current systems in the bedrock and all that kind of stuff, because that's going to be the next space weather, or the next course. We didn't get to the power system. We didn't get to conductivity in the ground, but there's a lot of work that's being done by the USGS. Yeah, a lot of good scientists working. This is such a funny course. So many disruptions. I'm glad it's all happening all at the same time. This is what happens when my daughter steals the last of my batteries. Anybody have a 12-year-old? They're wonderful, but oh my goodness. So I had no new batteries, so I'm having to kind of swap them out. So we're almost done. I think these batteries will last the rest of the time. But anyway, as I was saying, the next course will be all about magnetically induced currents and power grids and some of the issues that we have. I might even bring up a good friend of mine named Roger Fenton, who has spent a ton of time talking to me and teaching me about power transformers and how they work, and also what reactive power is. That's a tough one, but reactive power is critical, and it's the whole reason why shutting down the grid during a big solar storm is not the answer. If anything, that will exacerbate the problem. And we'll talk more about that next time. But right now, I guess I will just kind of open the field for questions, and I'll take a little bit of questions, and then hopefully, before my batteries run out, we'll say goodbye, and we'll just have to wait for the rest of it to be done in the next Q&A. So, questions? Mike Mosquito, dating bot, what's next? I know. It's crazy, isn't it? Oh, and we had a person who was trying to get a hold of my husband coming in to ask me, where is he? Because she thought he left the house. Like, no, I had to run and go find him. You should have seen the look on his face. That's going to be funny. All right, anyway. Okay, loud and clear again. Good. Got to watch those battery. Yeah, I know, those battery pinchers. That's what I'm going to call her. She's got an Oculus, and so she steals my batteries to put in her controllers. It's very frustrating. She uses AA just like I do. So my batteries get pilfered, and if I'm not paying attention, they're all gone. And I'm like, oh, what do I do? So that's what happened to me this time. Okay. Thank you, Tom. It says, thank you, Dr. Scove, and all the moderators. Yes, thanks. Big thanks to Mike and Jerry. You guys have kept me honest and helped moderate. I did see a few, comments that were taken away and were inappropriate. So I really appreciate it. They're the ones that keep everything on topic and prevent things from going awry. So let's see. Any questions, guys? Is there more crime when there's a full moon? Oh my gosh, the people to talk to regarding that are people in the emergency room, and it's what they call stress wards, medical stress wards. And the answer, overwhelmingly, this is anecdotal, but the answer is yes. If she's 12, can she join the Civil Air Patrol and have a pilot's license before a driver's license? Oh, don't tell her that. She'll probably try it. She's amazingly adventurous. So why no KP of 10? That's what HP is going to do. They've at the time, I don't know the history of why KP only went to 9. It's probably because it's the standard as Bartels. And why do they not change that? Why do they not change that? That is because of historical records, right? The problem that we have is that once we freeze an index, we create an index and we freeze it. And that's one thing I didn't show you. I'll show it to you, I think, right now. Do I have AA? Yeah. Once we freeze an index, it becomes unbelievably difficult to change because, and a lot of people would rail against it. And the reason for that is because we want to be able to go back in time and compare historical storms and historical events at Earth to the modern day, right? So the classic index, I think is one of the longest one running, is the AA index. Look at this, from 1868 onwards, okay? There are only 2 stations. Right, that's it. But this index, which would be by modern standards completely useless, is the only one we have that goes back that far. So therefore, we keep it going. So that even if we have KP and we have all these other indices, if we have the AA index as well, then we can go back in time to previous events that had a very similar signature in AA as a modern day event does. And then we can look at some of the other indices that are more telling. And in a sense, we can then extrapolate what that historical event must have been like. And so in a sense, we're doing forensics. It's like, space weather forensics. We're trying to glean more information about historical storms and their impacts on the infrastructure of the day. But we have to have our control, right? We have to have some constant that links that day back in time to today. Right, and so that's why we do this. So when we get these indices that are set up a certain way, and they become such a huge part of our history, of our vernacular, of our space weather vernacular, then it becomes really impossible to change them. And so we just have to add a new index so that we don't muck up accidentally our connection with our past, with space weather. Okay. Eventually, that won't be nearly as big of a deal, because as we end up having hundreds and hundreds of years, wouldn't that be wonderful? Hundreds and hundreds of years of high resolution space weather data, then, we'll have enough information to go back hundreds and hundreds of years and still have, really good resolution and really find, a lot of data from different monitors and different instruments, both ground-based and space-based. And I can't tell you, some of the biggest problems that we have when people ask about historical storms is that we want to go back and take a look at them, but we didn't have SDO, we didn't even have stereo, right? We didn't even have GOES or any of the data. We didn't have SOHO, right? We'd have the SMM mission, or we had OSO 7, which was only a coronagraph, and you find very quickly how blind you get. I mean, you only have to go back a couple decades, about 20 years, and space weather is incredibly blind. Prior to SOHO, we had YOCO for a little bit, which gave us a little bit of information in X-ray, and let us know that coronal holes were a thing. We didn't know that before. And filaments, as well as other big phenomena. This is all the stuff that I talk about in the coronal mass ejection mini courses. It was just this amazing period of discovery. But you don't have to go back very far before we really are blind and we had no idea what was going on. Just postulations and theories and eclipses, because that's really all we started with, right? So that's why the indices, there's no 10 in KP, and there never will be. But there'll be a 10 in HP, right, in the HPO indices. Hopefully that answers that question. Perseids, the meteor shower is on the 13th. Awesome. That is, where are we in the, I'm trying to remember. I just did a forecast, and I can't remember where we are in the moon phase. We're coming up to a full moon, aren't we? So shoot, that's still, I think on the 13th, we're still going to be a little bit of the moon. I think it's going to be waning. So we'll be waning toward a new moon, but I don't think we'll be quite there yet. But that's awesome to see, to know. Maybe I should mention something in my next forecast about it. Any other questions, guys? Oh, here we go. Does solar wind's temperature, speed, and density impact the KP index? Yes. The temperature, not so much. Speed and density, absolutely. What impacts most, of course, is whether or not the magnetic field of the solar wind is negative or positive. If it's negative, yes, impacts it quite dramatically. Obviously makes it go up. And even if you have a cross field, so what we call the BY component, even if you have a strong BY component, you can get KP to go up. Because believe it or not, BY can couple into and create strong currents inside the Earth's magnetic system. And it's not quite as dramatic as having a southward directed, meaning a negative BZ, but it does impact it, and it can drive aurora, believe it or not. And that's even when there is no Z component of the magnetic field. But then add density and speed on top of that, and yes, if you have a solar, with rule of thumb is if you have a solar wind speed of about 400 kilometers a second, you can get active conditions and above. Typically, if you're below 400 kilometers a second, KP probably won't make it to 4. Sometimes you can if you've got really high density, but not necessarily. Only if you have extremely strong magnetic field that's southward, can you get KP to really bump up when the solar wind speed is slow. If you have high solar wind speed, 5, 6, 700 kilometers a second, it doesn't take much, just a couple nanotesla southward, and you can get up to active conditions. So it really is kind of a trade space, right? I shouldn't call it a trade space, but it's really a function of it's a multivariate, what we call a multivariate process. You have density plays a role, but it's not the only thing. Speed plays a role, but it's not the only thing. And magnetic field plays a role, okay? There are other things that play a role too, preconditioning, other things like that, but that gets a bit more complicated. Hopefully that answered that question. I know it probably didn't make it that much clearer, but it's always on a case-by-case basis, sadly. It's partly why we still need scientists in the loop very, very often to really make sense of space weather. Can people see Polaris in Australia? I don't know. I don't know right now. Sadly, I'm not an astronomer. That's not my field. I study this solar system. I don't really look much beyond it. And that's one of the things that people kind of misunderstand. They think they can talk to an astronomer about space weather. Don't. Please don't. They know more about other stars than our own when it comes to transient events like space weather. They may know the lifetime of the star. They may know the convection under the surface. They may know, when it's going to go supernova or if it's going to go supernova. They may know a lot about those fundamental processes. But space weather, that's its own field, and they will likely think they know everything about space weather, and they know enough to be dangerous, not enough to be right. You really need to speak to a heliophysicist, and a heliophysicist, if they're worth their salt, they will only speak to the discipline of heliophysics that they understand, right? How many times have people heard me say, "Oh my goodness, that's an area that I don't know very well," and it's in heliophysics, because you can get a PhD in half a dozen more than that, probably. Oh my gosh, do I dare say 25, 30, 100 disciplines in heliophysics alone. There are so many ways to get a PhD in this field and know just a tiny amount of the whole picture, because it's really just that complicated, right? And I try to teach it, but I try to teach it at a top level. Okay. Oh, thanks, Mike. Thanks for answering that. I appreciate it. See, there's a lot of astronomers and either amateur astronomers or even professional astronomers that can answer these questions a lot better than me. Because I will tell you, I'm the first one to say when something's beyond my expertise, I am very humble about that. I don't BS anyone. I really don't. And if I have to speculate, if you guys want me to speculate about something, I will tell you up front, okay, this is my speculation. I may be pelted by olives, with olives by my scientific colleagues, but I'll say this is not my expertise. So I'll give you my best shot, but I don't know for sure. Oh, there we go. Thanks, Chris. You can use the Southern Cross. Good. Okay. All right. Any other questions about space weather, guys? I know Lourdes had a question about new findings and reconnection. I haven't had a chance to research that. I want to research that. And I also needed to ask you, Lourdes, if you're asking specifically reconnection in the Earth's domain, which I imagine that's what you're looking at, or are you talking about, like, let's say the switchbacks in that solar probe found, and that solar orbiter and solar probe are kind of working to understand more of, meaning the inner heliosphere, the solar wind, way in the inner heliosphere, out to like 20 or 40 solar radii out, because there's a lot of reconnection that goes on in that regime that we never understood until we flew these missions. We never understood actually occurred that far out. So reconnection happens all the time in so many different ways, in so many different places, and it's far more common in the solar wind than we ever realized. So I need to get some more details from you as to where I focus my research. Okay, any other questions, guys? Because I think I covered pretty much everything. I'll see if there's any more questions on Patreon, and if not, I will bid you all a good day. Thank you for hanging in there with me. This has been a very intriguing one. Oh, does anyone have a link to the HPO index? David, I'll go back to that. Yeah, hold on. Let's see, Vince is watching on the YouTube feed, David, and I'll put a link up there. And let's see if there's any other comments or questions. Noi, I hope you're here, Noi. I didn't see your name, but hopefully you're here. Okay, I think I got that. Good. All right, so let me go back to the HPO index. And it's on, I have it on the, no, where are you? There you are. I don't know if you can see it. If that's too small, let me escape here. I'll just zoom it in. I'll move this up. Slide up. Bigger. Here we go. There's the link. Okay, so HTTPS :/www.gfz or GFZ -Potsdam potsdam.de/en for English /HPO-index. And they do have, oops, I'm sorry, I'm pointing at stuff that isn't even there. They do have what that website is like I said, they've done an incredible job. They've really good attention to detail. They have it in multiple languages. So it's definitely one that you should go take a look at if you haven't. So much good stuff there. Okay, but that's the HPO index, and yeah, if you use it, tell me what you think. I definitely would like to hear about it. Okay. Any other questions, guys? My batteries have survived. We've all survived this this particular version, this particular course. Let's see, Julian. Thank you for this mini course. So many surprises. Oh, good. And Lourdes, you are here. Okay, at Earth's level, inside the slinky. You want to know in the heart of the Earth's magnetic system, so not necessarily in the front of the magnetosphere. Okay, well, we will have a call, you and I. Lourdes is one of my VIPs. My VIPs are like family, even a tighter family than everyone else. So they have direct access to me. So I will probably get on a direct call with her and with you, Lourdes, and chat it. Oh, thanks, Jerry. And chat with Lourdes. I'll also chat with you about it, okay? And we can go over some of the research together. And Jerry, that's thank you for posting the link. I appreciate that, so people can see it and click on it. One thing I will say, Lourdes, is that Erica is, Erica, who's a fan of yours, Erica Palmario. She did lament about the new decadal study scientists that have been appointed to that decadal study. And she has a right to lament. She's a solar person. And so, of course, anytime solar physics is not well represented on the decadal study, that's going to make solar people angry. But it's probably well-intentioned because, we have solar probe and solar orbiter, and really soon we're going to get the L5 mission, which is also going to be a sun-based mission. And we still have SDO, which is a fantastic mission in of itself. And the magnetospheric and ionospheric groups have not been doing so well. So believe it or not, over the next decade or more potentially, we're likely going to see a bit more influence from the magnetospheric and ionospheric groups, the disciplines, for missions. So we might start seeing more, successors to missions like MMS, which I know you were super excited about. And we're going to potentially see maybe more CubeSat missions, maybe down in Leo, or even CubeSat missions that are going to other orbits that are going to be doing more constellation work to be able to understand reconnection better. Because really, that's kind of what we need anymore. To understand reconnection better, we're having a hard time doing it. We can't do it with single spacecraft. We have to have multiple spacecraft to do it. And the more, obviously, people are going to say the more the merrier. But the commercial entities have shown us, that these constellations are completely possible and very doable. And there's going to be a lot of lessons learned that I think the scientific community can benefit from. So I would not be surprised in the next decade if we start seeing these constellation missions, magnetospheric constellation missions coming out. Be really cool. So a lot more work on reconnection coming. Okay. Oh, good, you are here. That was amazing. Thank you so much for bringing these things I've been struggling to understand for years. Oh, I hope I have. I hope I have. That's so wonderful. Okay, great, and good to see you here. Luke says, thanks for your time and knowledge, and thanks for the Potsdam page too. Yes, see you on the next one. Okay, wonderful, Luke. Thank you. And oh, good Lourdes, you got the comment. Why is the Earth speeding up? I have no idea what you're talking about. Speeding up what? In its orbit around the sun? I doubt that it is. If anything, things, if it is, it means it's spiraling into the sun and we're not going to last long. So I doubt that's happening. Otherwise, that would be making headline news and people would be getting Nobel Prizes for that type of thing. If it's speeding up and you're talking about rotation, that's not happening either, because the moon is actually slowing our days down because it's of its gravitational load on Earth. It's actually slowing Earth's rotation down, believe it or not. Okay. Okay, still excited about MMS. I understand. Like the cluster and Themis missions, exactly, exactly. Cluster and Themis have done. They were really the I don't want to say proof of concept because they were far more than that, but they really did prove that we could learn so much more from about reconnection and those processes using missions that were closely clustered together. I mean, that's the whole name of cluster, closely clustered together on different length scales, because we have to understand these things on with a knowledge of different length scales. Reconnection is such a small process, and there's all these little magnetic islands that occur, and so reconnection is kind of it's not like a finite single thing. I don't want to say finite. It's not like it's a smooth process that is occurring everywhere at the same place at the same time in the same way. It's really not. It's very I don't want to say stochastic either, but it's very patchy, and that's part of the problem. Is it's very hard to catch. And when you fly through a patchwork quilt, you may catch it, you may not. You may get this little bit, that little bit, and these different bits in different places at different times look different. So how do you compare them? You can't. So that's why missions that have more than one spacecraft, you need multi-point measurements to understand this stuff. And that's why constellations will be so useful, so that we get a much better understanding and extent of the type of reconnection that occurs. And it just is, it's length scale and time scales are so critical when it comes to reconnection. So hard to deconvolve. Okay. Anything else, guys? Looks like we're good. Let's see, wild spirit. I just call you wild spirit because I always get stuck on alchemical. I think it's due to the precession of Earth's wobble. Well, that's true. I mean, there is some oblateness. So we are fractions of a second off. Yeah. I mean, things don't, Earth is a reasonably rigid rotator, but you want to get really scary. I mean, it's essentially a rigid rotator compared to the sun, right? The sun doesn't rotate. It's a differential rotator. It actually rotates faster at the equatorial region than it does at the poles. So, you want to talk about, if you wonder why I don't get spun up, pardon the pun, about Earth's, rotation rate changing or anything like that. That's because I study a star who can't even make up its mind how fast it wants to rotate. From the equator to the poles, there's days of difference. And even gas giants like Jupiter, same kind of thing. There are all these weird patterns where, a body, just because it's a rock, essentially, doesn't mean it has to, all parts of it has to rotate at the same speed. There's all sorts of different things that are, and forces that are pulling on it, that are causing it to wobble or change. And we have so far to go to understand all these processes to the level that we need to understand them. We can postulate things, but we don't know the details of all of it yet. Because I know somebody's going to throw in there, well, how about the Earth's magnetic field and the coupling to the sun and the planetary tugs? How much do they affect things? Because they affect things. And, and it's like, yeah, likely, but can we quantify it? Not really, not yet, because we don't even understand the primary processes well enough yet. We don't even understand how a mountainous region causes things to wobble because it throws off the gravitational constant. I mean, it's just, or I shouldn't say the constant, the gravitation, the center of gravity and things like that, and the local gravitational pulls. So there's just so much, there's so much detail that has to be sussed out just in the processes that we do understand, to be able to uncover then and subtract that stuff out so that we can attack the processes that we don't understand so well. And that is, those types of things are not low-hanging fruit. So you're not going to get scientists to do that anytime soon. They can't get funding for it. All right, guys. Looks like we're pretty much out of questions. Thank goodness, because my voice is going. Lol, it can't make up its mind. Exactly. Yeah. The sun is a trickster, I tell you. Okay, guys. Yeah, thank you so much, Jerry. You've said it very properly. Thank you so much for joining me, and I hope this was a useful class. We will begin next time. I'll go through a slight review, and then next time we will. The new material will be really focused on GICs. Okay, and I might even go into a case study. Maybe I might go into the Kaplan study of the 1989 event, since we brought that up, and that's such a common event, and that's really kind of what our standard candle was when it came to geomagnetically induced currents. It really woke us up as a nation and as a hemisphere, the Western Hemisphere anyway. So it's a very useful case to study. Okay, guys, so glad you had fun, and thanks for joining me and dealing with all of my little disruptions. Okay, guys, take care.